just wait a while. I'm testing that everything works on my end. We will start soon. Oh yeah, um, I am ENTL. I am a former participant in the International Physics Olympiad. I participated last year, and sadly my country didn't participate this year, so now I will be doing a Livesolve. And the point is for me to show like how I personally approach problems and what I think when I see the problems. This year's problems are difficult. I think they are the most difficult problems in the International Physics Olympiad ever, just by looking at the medal cutoffs. So hopefully I'll be able to do something, but we'll see. And I want to just mention that I have been sick for quite a while, so sorry if my voice sounds a bit funny. And also, I still have a bit of a cough, so I'll try to mute all my coughs away. But if any slip by, I'm sorry. So anyway, so let's first start to look at the exam. I have copied the physical constants here, but they are on my second screen. But anyways, I will open the problems. So here I have just, yeah. So the first problems is about magnets apparently, and the first thing when you get an exam is to look at every problem and think where you want to start. So I know that personally that magnetism is my weakest topic in physics, so I would probably not start with this one. But here we have like cylindrical magnets and some sort of magnet chain just by looking at the pictures. Then we have some sort of spherical, yeah, we have like field lines, and then we have some sort of a grid of magnets, and we have to do something about that. Then the second problem is about James Webb Space Telescope, and this is bad for me since my second weakest topic in physics is optics, as in geometrical optics and wave optics. So this exam would not fit for me, and because of that, it's a perfect practice exam for me. And the third problem is about different topics in physics. Here is two mechanics, one relativity, and one mechanics again. So I would probably start with this problem, but for this Livesolve, I'll be going through them in order. So I will start with the first problem. So, and also I'm not doing this blind, as you can see. I have seen the problems before, but I have not attempted them before. But I have had time to process the problems, to think about how I can approach it also beforehand. So anyways, let's read the problem statement. So here we have we are said that the magnetization J can be assumed to be constant, over a wide range of applications, and we assume that J is 1.5 Teslas per mu naught, and the magnetization of all the permanent magnets is homogeneous. And here we also given the definition of magnetization, which is good, especially it would have been good for me since I would have not known about this. I rehearsed magnetism yesterday, so I know now a bit more about this topic than I would have known. But yeah, the magnetization is defined as the volume density of the magnetic dipole moment of the matter. Then we are given 4 hints. These hints are usually extremely valuable in the International Physics Olympiad, as they tell you something about the approach you are expected to have, and in that way you know what to think. So we have some kind of series given. This is typical for International Physics Olympiad as well, as series is not a part of the syllabus, so they don't really expect you to be able to determine this series. But in some problem it can be useful. Then the magnetic field created by a spherical magnet is identical to that of a point dipole. The magnetic fields created by magnets of all other shapes become equivalent to a point dipole fields only at distances much larger than their diameter. That is a good thing to know. Then the third hint is that electric and magnetic fields of electric and magnetic dipoles as function of coordinates and of the corresponding dipole moments are similar, i.e. one can be obtained from the other by multiplying it by a constant factor. This is also really good because most people, including me, are much more familiar with electrodynamics, or more like electrostatics, as in more familiar to work with electric fields than magnetic fields. And the induced field due to a boundary condition can always be replaced by some configuration of field sources outside the given boundaries. So this basically is the uniqueness theorem, and this tells me that in some problem we want to use an image charge or an image magnet. So yeah. So the first one is interaction of magnets. When the distance to a magnet is much larger than its size, the magnetic field created by it can be approximated with the magnetic field of its dipole moment. Like that. And here, and yeah, there's just good information to know, so we don't have to memorize the magnetic dipole field. So I'll just screenshot the first problem, and let's go to the whiteboard and let's start to solve. So actually I'll take this as well. So that's a bit too big. So let's put that there. So find the magnitude of the interaction force between two coaxially placed cylindrical magnets of diameter d and thickness h, magnetized parallel to their axis. If the distance between the centers of the magnets is L, yeah. So you may assume that L is much larger than D and H. And I'll just write the definition of J here. So the magnetization was something like this, where this is the magnetic dipole moment. So because we are given that L is much larger than D and H, it usually means we can do some approximations. And in this case, let's see, because, well, first of all, we want to find the magnitude of force. And there's not really like a good formula, or there is, but there's not really a good formula for force with magnets. So you want to find the energy, which is well known with dipoles. So we have the magnetic energy is something like minus m dot B, and then we just differentiate this to get the force, because the force and the energy, actually I'll use W for energy because E looks a bit too much like electric field. So the force is given by the is more or less given by the gradient of the energy. So this is good, and actually now we are pretty much done. Because now I have already an approach. What we have to find out is the magnetic dipole and the magnetic field at the magnetic dipole. So because it is very the distances are very large, I can just imagine these to be point dipoles. And hi to everyone who is saying hi in the chat. So if I just redraw this situation, I have a dipole here. So it is this magnet. Then there's the distance L, and we have another magnet or dipole here. And in between we have the distance L. And now we just have to find out what is this magnitude of the magnetic dipole. And we already have been given previously, I forgot to take a screenshot of that, that J is 1.5 teslas per mu naught. So yeah, so and we are given the definition of that, so we can just solve the magnetization to be the two greater than signs means just that it is much greater than. That is usually used in the context of making approximations. You will see how I'll use this probably in some other problems, because the International Physics Olympiad loves to have approximations, since physics is just approximating things until it is mathematically solvable. But anyways, now we can solve the magnetic the magnitude of the magnetic dipole. So that is M is J V, where V is the volume, and then we are given that these are cylindrical magnets, so we just use the formula for a cylinder. The diameter is D, so we know that the bottom of the cylinder has an area of pi over 4 D squared, and it has a height h, and then we have this J still. And now we could solve for the... Actually, I think it's good to solve for the numerical value now, because I think the formulas will get quite big if I don't use just m. So let's calculate that first. So we have pi and pi over 4 d squared by h. Well, what am I doing? D was 20 millimeters, so that is 0.20 meters squared times 2 millimeters times 1.5 teslas per mu, and mu was, I think it's like 4 pi, but I'll check. Yeah, 4 pi times 10 to the negative 7. And what are the units? Newtons per ampere squared. And now we just plug, this is actually, you can do this in your, without a calculator, but I'll just use a calculator because I want to make sure that I do everything correctly, and you have a calculator in the International Physics Olympiad. So I'm using Speed Crunch for this because I like it, and that's what I use at school as well. So no, 1.5 divided by 4 times 10 to the -7. So we get 0.75, and I could look at the units. But I think I remember the units, or do I? The units of magnetic dipole moment is something like, isn't it just like, well, I know that the magnetic dipole is given by this formula for like circular currents, so I immediately see that it is amperes per meter, ampere meter squared. So I think so. So am squared. So I'll have 0.75 amperes meter squared. So now I found the magnitude of the magnetic dipole moment, and then we just have to find the magnetic field given by one of these magnets to the other, and we already know that the magnetic fields look something like this for a dipole. So, and because these are directly opposing to each other, the relevant magnetic field line here is this one. And because we are given here in the problem statement that the B field is given by this, where the M parallel and M perpendicular are the respective like decompositions of the the dipole moment vector to the line connecting the 2 points. So we immediately see that if we have here the line connecting the 2 points, this magnetic dipole moment doesn't have any perpendicular decomposition. So this formula here above actually just gets immediately rid of this. So I can now say that it is m times, now immediately I lose sight of this, mu naught over 4 pi, and the distance between these two is L, so L to the third power, times 2m parallel, but because in this case the parallel component is the entirety of the vector, we can just say that this is 2m. So now we have this dot product between basically just m and m, so that it gives us m squared. So we have minus mu naught m squared over 4 pi L3. And now I can just plug everything. Actually, I don't plug anything yet because we didn't want to find the energy. As I said, I want to find the force, and force we get by differentiating this with respect to some coordinate. In this case, the distance between these two. So now the force is minus dw dl, and actually because we only care about magnitudes, I can leave all the minus signs out here because here. And this is easy to differentiate. We get because you can rewrite this as like this. So you get 3 in the front, mu naught m 2 over 4 pi L4. And I think that should be actually I made a mistake here, I think, but you notice that I have lost this 2. I was just looking at the the steps I've done. Here I have a 2, and then I get rid of it. This 2 actually cancels out with this 4, such that we get a 2 in the denominator here. So we actually get 3 over 2 mu naught m2 over pi L4 for the magnitude of the force. And actually, let's do something like this. And then we just have to plug everything in. And this is what I was saying. It is good that we calculated the m immediately, because if we plug this expression into the m squared, this would get a bit messy. So now we have everything once again. 4 pi times 10 to the negative 7 newtons per ampere squared times 0.75 ampere meters squared, all squared, over pi times the L. I have the problems on my second screen, but I'll show it to you as well. L was 20 centimeters, so 20 centimeters is 0.2 meters to the 4th power. And then I'll just plug everything to the pi's cancel out. That's also nice, but that wasn't the point. I'll get 3 over 2 times 4 times pi times 10 to the negative 7 times 0.75 to the 2nd power over 0.2 times 4. Is everything correct? Let's check. Because I think my expression is correct. The thing is that with my experience, I always mistype something on the calculator and lose points because of that. So I'm getting paranoid that I'm doing something wrong somewhere. So let's make sure that this actually divides. Sorry, I had to mute. I coughed. Hopefully my voice is yeah. So well, I don't want to get to lose to get stuck on this. I'll just get this is what so 0.66 millinewtons. Let's do a final check that everything is correct. For 0.75 ampere squared, I have put that into the square, and minus 7, 4 times. Oh yeah, I put the pi there, but I didn't put it on the denominator. Quick moment. I just check. Okay, so I am muted once again. I thought I muted myself, but yeah, thank you, anyone. I don't know where I muted myself, so I'll just recap everything I've said in like the past 5 minutes to make sure. I was talking about the significant figures and how you round things in the International Physics Olympiad, because and once again can before I say anything, I'm sorry that I'll mute myself. I'll mute myself every time I cough, but sometimes I'll forget to unmute myself, and I think that's what happened. Um, anyways, um, the significant figures in the International Physics Olympiad really don't matter in the theoretical exam. They don't care how you round it unless you round it too much. So you want your roundings to be precise enough. So if I look here and think about the traditional rules, I have a measurement given in only with one significant figure, but I'll round with two because a good rule of thumb in the International Physics Olympiad is to give at least two-digit precision. And if you don't, you may lose points. And you want in the International Physics Olympiad to get every point you want, because every point is really, really well, because it's really hard to get points in the International Physics Olympiad. If we look at this problem, it's only 0.6 points. So yeah, and I'll try to solve all the problems. I just but that means that I really have to up my pace. So but I want to explain my thought process as much. So in the beginning, I want to explain as much as I can because I'll use the same deductions afterwards. But yeah, so sorry that I was muted. I left my mic muted. So I'll try to check every time when I mute myself that I also unmute myself. So at distances much larger than h2, h over 2, the field created by the magnetic by the magnet from task A1 is the same as that created by a circular current I. Find I. Well, this is a quite easy problem, I think, if you know like the basic things from magnetostatics. And that's what I did yesterday because I knew there would be some magnetism involved. I'll try to do something like sorry. So the thing is that if we think about a cylindrical magnet, I'll try to explain this theory a bit. We have a cylindrical magnet. I'll just draw it like this. And from above, like this. The thing is that it will have the magnetism in a way is created by some like current loops inside the material, or you can model it like that. But the thing is that it is current loops here, and it will be a magnet when these current loops agree with each other. If they are in any way, like if they are opposite to each other, they will just cancel out and you won't have any magnets. But you will have like current loops like this. But you notice that inside the material, these loops cancel out. So if I make them like squares, like this, you notice that here the current will be in this way and here it will be this way and this will cancel out. The only place where you will have these currents is outside, so at the surface. So when we think about it, we will have like currents going up this because the magnetization vector was in this direction. And when we are in a distance much larger than h over 2, which is like the half of the thickness of this material, it will look like this has no thickness at all, so we will have only one current loop. something like well, it is always difficult to do loops because other people will look at them in different ways. But anyways, we will have some current here and a magnetization vector like this. And the magnitude of this magnetization vector is given by IA. And because this loop has the same dimensions as the cylinder, this A is just a pi over this area is just pi over d. No, pi over 4 d d squared. Yeah, I think so. And then we can just solve for I, and that gives us 4 over pi d. No, no, yes, no, yes, yes. 4m. I'm always so paranoid that I make some algebra mistakes because I've lost so many points due to that before. So I'm just making sure that everything is correct. Yeah, I think so. But no, wait. And yeah, and then yeah, of course it is correct. Then we can just substitute everything in. But I think because m, if we look at m, m has a really similar thing here because it has the area as well as the h here. So we will actually I'll simplify this a little bit of the formula because this m will be ahj is equal to ia, and this a's cancel out, so we just get that I is hj like this. And then we just substitute the values given to us. H was let's see here, h was 2 millimeters, so 0.002 meters times 1.5 teslas per mu naught, which is 4 pi times 10 to the negative 7. What was it? Like amperes per newton or something. I'm really bad at memorizing units. Newtons per ampere squared. So that's good that they give in the physics Olympiads, they give these units to you on there. They give the constants to you, which have the units. So that really helps me. And then we just substitute everything into the or put everything into the calculator. And if you're wondering about my weird notation, I'm doing. Wait, that sounds a bit high. Well, okay. Apparent because I don't see any room for error here. I think that this should be something like 24,000 amperes. Apparently, I didn't know that these current could be that high in when you replace these. Because I haven't done a lot of problems in electrostatics or with magnetism in general. I have really bad intuition, so I will second guess myself quite a lot, and then I'll pick up the answer sheet again and take the yeah, hello people who have just joined. Then the formula was just JH, and the value was 24,000 to 2,400 amperes. So 2,400 amperes. Anyways, then we had the and about the structure of the International Physics Olympiads, um, because I think this might be interesting for people to know that then because you see that we get only like few points here. But these problems usually get much more difficult, so we have much higher points further down the line. But the reason why they give you these really easy problems is to lead you in the right direction, because they have to correct or grade or like how many people participate, over 300 papers in just a few days. So they want that people have at least somewhat the same approach to the general problem, because this is basically just one big problem, part A, but they give you like the steps through the subtasks to solve the final one in a way. So in that way, they assure that everyone has more or less the same approach to these problems. So you should always think that what you have done is really relevant to what happens later. Uh, so, anyways, A3, find the interaction force between the magnets for the setup of task A1 if instead L is equal to 5 millimeters. You may assume that D is much larger than L is much larger than H. And actually here we have been given that at distances much larger than h over 2, the field created by the magnet from task A1 is the same as that created by a circular current I. So this means that I will actually just have here two current loops between each other, because this L is still much larger than h as given by the problem statement. So actually, instead of having to analyze this rather complex situation, we can just look at two current loops next to each other with distances is 5 millimeters, and we have solved for I already before. So now we have two currents next to each other, and they have some force, and there is a well-known formula for this, but I don't remember like the magnetism formulas at all, so I have to derive this. Maybe this will be useful for someone. But first of all, we have to derive because this will have some magnetic field, and this magnetic field is given, and also D is much larger than L, so I can actually assume that the effective force is the same if I open these current loops to give straight wires of length D, not length D, length what is it, 2 pi D over 2. So P, yeah, P dot, yeah, that's the definition of pi. So length of pi D. So anyways, I'll have to find the magnetic field created by this. Because I don't remember these formulas at all, we'll just use the Ampere's law. Oh, no, not like that. Here is a current coming at us, and I'll make a circular loop here and then apply, and then we'll go like this, and due to symmetry I'll know that the magnetic field line or the magnetic field is constant along this, so I'll just have pi times d L over this loop, let's call it P, not L for loop, L, and that'll be mu naught I, yeah, I, and actually we will just have why I opened the loop, you'll say, you don't really have to do that, it's easier for me to think. You'll see soon. Anyways, then we will have the dl, the length of this is just 2 pi r, b, and mu naught I, and then we'll have that mu naught is mu, or b is mu naught over 2 pi r. Actually, I should have remembered this, but I forgotten it. So now this will have, this current here will give us a magnetic field lines here coming at us, and this will have a the force is given by IL B because these are perpendicular, and the length here is just pi d. So I have I pi d, and B was mu naught I over 2 pi the distance between these, which is L. So I'll mu naught d I squared over 2L. So let's check that everything is correct. Unfortunately, you don't see my cursor, so you don't see what I'm looking at here, but yeah, everything seems to be correct. If you remember this formula, like on the like, if you just know this by heart, then you wouldn't have done all the steps I've done. But I hate to memorize things, so I memorized the absolute minimum. And then just derive everything, which is not really good for competitions, but that's good enough. And then we will just plug everything back in. So we'll have 4 pi times 2 minus 7, was it newtons per ampere squared, times d, I don't remember again, what was it? Oh yeah, I have it here. D is 0.02 meters, 0.2 meters, times the current we had before, which is JH. Actually, yeah, it's JH, the current. So I can actually reform it like J squared H squared to L, because then the mu naught cancels out. Because then we will have 0.02 meters times 1 point. Actually, it won't cancel out. Okay, then 0.5 Teslas squared times the height of the cylinders, which was 2 millimeters, times 0.002 meters squared over 2 times the L. What was the new L? That was 5 millimeters. So 2 times 0.005 meters times, now again mu, because of the cancellation with j, j, 4 pi times 10 to the negative 7, and the units, but I'm too lazy to write out the units anymore. Probably bad for when they are trading these things, but I don't care. I'm the one who is going to grade this afterwards. I'll post the results of the points I will get. But it's important to remember that those are not the points that I would have gotten if I had participated, because I am I already have seen these problems before. This is the first time I do them, but I've seen it, so I knew what to expect in a way. So this is not for comparison, but just as an idea of what we do. So yeah, 14 newtons, and then I'll put and of course I have like unlimited time here, so I'll have to find the answer sheet once again. I have unlimited time here technically. I try to keep this like in 5 hours, but because I'm speaking, there's quite a lot quite a lot uh, quite a lot I am losing. I lose quite a lot of time. Sorry, I was too deep in thought. Wait a second. I'll drink something. And yeah, I haven't muted my microphone, so that's good. Yeah. Then, second problem. Not second problem. Fourth problem. Identical spherical magnets of diameter delta is equal to 5 meters bound together by magnetic attraction form a chain. What is the maximum length L for such a chain which does not break under its own weight when hanging beneath the topmost magnet? The density is given. Okay. Now this is like the first true problem, I think, here in this or in this part. The other ones were just warm, and they have given us some clues as to, for example, how to find to as to find as how to find as to how to find these forces. Basically, that's I think that is what they have wanted to basically give us here. So actually, what we were given previously, I remember, is that they gave us that the magnetic field created by a spherical magnet is identical to that of a point dipole. The magnetic fields created by magnets of others, yeah. So it's so we will have point dipoles here exactly. So basically, we will have a magnetic chain like this. I'll draw these magnets, and it will continue for some time, and every single one of these is a magnetic dipole. It doesn't really matter what way they are pointing, but they are basically pointing in the same direction. And we already found, and because they are pointing in the same directions, that every time a all the field lines relevant to this problem are on this line, and they point along this line. So actually, the force between any two magnets in this chain is given by the formula we proved for A1. 3 over 2 mu naught n2 pi over 4. So let me copy it if I can. Like something like this. Yeah, I'll copy it to here. This is of course easier to do when you are doing this on paper, and then it copied that. Well, okay. I'll just what was it? 3 over 2 mu naught m squared over 2 pi L to the fourth, and that is the force expression we had. And now we have to think a little bit about the physics here, or have some physical intuition here. So if we are basically keeping this magnetic chain here, so we keep a hold of this ball, where will this magnet chain break when we add that last bit of straw? So that will be with like physical intuition here. That will be at this point. So all the magnets below that will disappear. What did I just say? I just said something without thinking at all. So when I'll add the last magnet and this will split, it will split here. And I know how to find the force. So actually, what will happen is that this magnet, if we look at the magnet chain here, I'll just write the magnet chain with like this. It will have some sort of weight, and it will have the magnetic force upwards. And these are equal for the limiting case. But how do we find this magnetic force going up? Well, now we use the Newton's third law, because it is the same as the total force, magnetic force on this first magnet. Yes, I am ENTL. So actually, I just have to find out what is the force in the limiting case to this topmost magnet. So let's think about it. The second magnet in line will give us a force of something like this. And what will be the distance between these two? It will be the diameter, because this distance between these 2 points is the same as the diameter of each of the spheres. So I'll have, for the first neighbor, let's put F1, mu naught m squared 2 pi delta, or delta to the 4th power. And then the second magnet will just have twice the distance. So we will have something like this. And the third one will have 3 times the distance, and the fourth one will have the fourth time the distance, and so on. So I will have an expression for the total force, which is like is this called an International Physics Olympiad easy problem level, or I am yet to learn? Well, I'd say that this problem is like a medium. This specific problem is like a medium problem in the International Physics Olympiad, because it's 1 point. Hard problems are usually like 2 points. That's probably like the max you will have from one problem, and the easy ones will have like less than 1 point, and the medium problems are usually in between this. That's how I usually perceive this. Anyways, we will have some sort of sum of these forces, and these all will have basically this term in common with all of these. And the only thing that is changing, so I can take that out of the sum, the only thing what is changing is this factor here, which is just n to the 4th. And this will start from some sort of 1, and this will end on n. And I think we can make an assumption here, or more like a good approximation. Because I think there will be much more than just one magnet on top of this. So we have to make some sort of an approximation here, because this will be really annoying to work with, and we have been given, if you remember, this specific exactly, use the math hint given. That's what I mean. We have the series given. So that's what we want to actually use here, I think, because we can assume that there's much more than just one magnet in the limiting case. So I can say that this is approximately equal. And in this case, I will use approximately 3 to the 2 mu naught m squared 2 pi delta 4th. And then we have the series here. And then I can just use the hint given, which is pi fourth over 90. So I'll have 3 over 2 mu naught m squared 2 pi delta fourth pi squared over sorry over 90 here. And then this will simplify a little bit. 90 is 3 times 30. So we will have actually 60 like mu pi mu naught and actually pi squared m squared 60. Why do I have 2 pi here once again? I don't think we should have 2 here. Yeah, so 60 times delta 34th. And then we have to actually find the m, because the m won't be the same. But once again, we know that m is equal to j times the magnetization times the volume, and the volume of this one sphere is 4/3 pi to the d over 2 cubed j, and we will see this will have an 8 here, so that will be 1/6 actually. 1/6 as a factor. There is not infinitely many magnets. We are doing an approximation because the exact solution would be impossible. We are doing a solution that there will be much more than one magnet. So we can in sort of approximate it as infinitely many, and that's actually pretty good approximation, because the farther away a magnet is, the less it affects the total force. So in a way, it really doesn't matter that we approximate it as a series. And yeah, then we have third here. So let's remember this. Actually, this might make the actually, let's just use mjv for now. J squared v squared is 60 delta fourth. And now that will have to be equal to the total weight of this system. And every magnet will have how do I say this? Every magnet, of course, has some weight attached to it, and we can find that weight. Let's use G, I for G individual, is mg, and this is now the mass, not the magnetization. And the magnetization, or the mass is given by rho v, and we just so we have rho vg. So in total, if we say that we have n magnets, we will have the total weight of the system will have n, or the part that is fighting our magnetic force is n-1, because we are keeping hold of the first magnet, so that can ride free. So we will have n-1 rho vg, and I'll just make this be equal to n-1 rho vg, oh, voice crack, mu naught j2 j to the second power v squared over 60 delta fourth I think. And these V's will cancel out in that manner. So we will have that n minus 1 is equal to pi squared mu naught j squared v 60 delta fourth rho g. And now we can put in the expression for v. Um, um, for v, which is pi over 6 delta to the third power j, because now we don't have to put it to the second power, which makes my life much easier to do. And j squared delta, actually we'll get oh yeah, what am I doing? Pi 6 to the delta pi 6 to the delta third over 60 delta fourth rho g. So we will have a total expression for here as pi squared, no, pi cubed mu naught j squared over 360 delta rho g, like that. And now the total length of this system is just n times delta. So n times delta. So we have the length is equal to n times delta, and we already know what n minus 1 is. Ultimately, it doesn't really matter if this because we are doing approximations, it doesn't matter if I use this directly or add 1, but I'll just add 1 to make sure. Plus 1 delta, and actually if I then have it like it is like this, and now I love how my G looks exactly like delta. So like that, and now I don't want to write the numerical values anymore. I'll just plug everything directly in. So we have pi cubed times well, I'll actually have what was j? 1.5. So I will have 1.5 squared divided by 4 pi times 10 to the negative 7th divided by, actually I can just put everything here as well, divided by times 360 times rho, which was where is my 7500 7500 times g. So I'll have that the length is 2 meters. I think I might have done like many mistakes down the line. I didn't take n-1. Why I took n-1 bolt's weight? That is because the first one is because we are keeping this first one, like, you can imagine if you have ever played with like magnetic balls, you keep the first one in your like hand. So ultimately the breaking point will be here, and it will break when the weight of this chain is the same as the magnetic force on that. And that chain will only have n minus 1 magnets if we have n magnets in total. Um, delta fourth, delta fourth, delta fourth. I'm just making sure that I'm not doing like any big mistakes here, which I have probably done quite a lot. Um, but I'll have this as my final answer. Um, I just feel like this is that I've again done some. Oh yeah, I also have to add the delta there, but you see that one delta doesn't really affect our final final length that much. I'm just worried there's a G missing here, that I have done again a mistake or two, but I don't see any like 36, 360. I think that is correct. Yeah, it is what it is. If I have done a mistake, then I have done a mistake. This is probably something. So it is 2.1 meters. Um, I am just pretty sure that. Because I have a feeling something is wrong. But if we think about, we have 2.1 meters. Let's just check one thing. 3.1 meters. Yeah, 3.2.1 meters. Yeah. Well, yeah. The approximation, I'm not really like, personally, I think I have done a mistake, because I will get that there will be only like 420 balls, and I wouldn't say that is very much larger than one. Yeah, it's like 400 times larger than one, but usually I'd like to it be like over 1,000 larger, because if we think about it, if I divide one by 420, it's 0.00. Yeah, maybe. Um, so I'm just checking. I think my expression for the force itself is correct. Um, or is it? Oh, well, what was our expression here given? Pi to the fourth. Why do I have here pi to the second power? First of all, that should be pi to the fourth. And here I have a mistake that this is pi to the fourth divided by pi is pi to the third. So I have pi to the third, I have pi to the third, I'll have pi to the third to all of these. So good that I found my mistake at least, because that is not often I find it that easily. Pi to the third, pi to the third, pi to the third. But this is no longer like physics. This is not really interesting stuff. This should be pi to the fourth. This is just algebra, and I think we are all here for the physics, so I should continue. It's 1 hour and I'm not even done with part A, so I'll try to be quicker. Let's say that. Be quicker. But the last problem, the part three, that seems to be like seems to be uh, much shorter than usually. So I think it would be possible for me to um, to skip a little, or not skip a little, to keep up pace. If I am, it's so hard to talk and think. It's possible to not be here for the entire night, or at least it's night for me, evening for me, right now. Yeah, now I have something much better. I have 6.6 meters. 6.6 meters, and if we now um, think about it, we have 6.6 meters, and we will have how many magnets? If I divide our result, uh, which is something like 6.6, if I divide that by 0.005, I have like 1,320 magnets. So that is much larger than one, let's say that. Anyways, then A5. These days are already quite a, at least if we look 1.5, this is like a medium, harder of the medium range. But funnily enough, I've no. So consider the chain from part A4, obtain an expression for the magnitude of the magnetic B field such that at such a point P, which is at distance R from one of the chain's endpoints O, and the single angle between the chain and the line OP is theta. Well, I think we have been given a way to calculate B given an N. But I think this will be quite a complex, not a complex integral, but mathematically much more demanding than international physics problems, international physics Olympiad problems usually are, because the problem should focus um, should focus on the physics, not the mathematics. So I think there should be a physical trick to this. If I cannot find any, I will do the brute force integration, but at least I know I have a fallback method. But let's think a bit smarter. Because in a way we can look at this chain, and from far enough, which we have been given, that this point is far enough. This chain of individual magnets would look just like a line with some sort of linear magnetic dipole moment density, and we could integrate over that. But we already know, given here, that the magnetic field created by a spherical magnet is identical to that of a point. And please, I know that these hints are given. The thing is, I want to show how I approach these problems. So I appreciate that you are saying that there is a hint given to this problem, but I want to show the thought process I'm having. So, then we have a dipole, and a dipole can be thought of as a limiting process of two monopoles. I know that magnetic monopoles don't exist, but mathematically it really doesn't matter if these monopoles exist, but they are always in pairs of two, such that they are always dipoles. So I can use this trick, and this is like really typical for Calder problems. I'm not sure if this is a problem made by Jan Calder, but when I was practicing for the European Physics Olympiad, I think at least in two problems I did, you had a good way to solve the problem was to split the dipole into two monopoles. But right now, uh, um, the thing is that um, the magnetic fields created by magnets of other shapes become equivalent to a point dipole fields only at distances much larger than their diameter. This actually means, in a way, that if I have two magnetic poles, not negative and positive, like south and north, like this, then this is basically just a magnet, but not the point dipole. But when this distance between these two is much larger, so when I'm looking from like this point here, um, from this distance, let's say L, is much larger than D, this will act field-wise like a point dipole. And this is due to something really interesting, because if we think about like electrical dipoles, the electric field due to a point dipole, so an ideal dipole, is something like k, which is a function of the dipole moment and the place we are looking at times r to the, not the electrical field, but the electrical potential times r divided by r squared. This is exact for a point dipole, but for a physical dipole, so a dipole which consists of two poles, actual poles, the expression is this expression here plus some well, not really. It will be this expression times d over r squared plus some terms of order d over r, where d is the distance here, d over r 3. So there are these extra terms, but when we are looking at a far enough distance, I can say this approach to zero much quicker than this. So this is like the only thing that matters. So I can, and we are given that this point we are looking at is much farther away than delta. So I can think of our spherical dipole as two monopoles, S and N, like this, with the distance delta. And if we think the second chain, or the magnet here, will have a south pole here and a north pole here. And the second one will have a south pole and a north pole. So we actually notice that these monopoles cancel out. The only things that are remaining is a pole at this end and a pole at this end. And now we can, and because I can say that L is much larger than R, this means that the field created by this pole here is negligible to the field created by this pole here. So I'll just have some magnetic line mu naught over 4 pi over 4 pi how do I over just wait I have to of q over r squared. I forgot how like fields work for poles for some reason. I had to think about the force. So this is like exactly the same for like electrical fields. We would have like 1 over 4 pi epsilon naught q over r squared, because it's a pole. And now I just have to find the magnitude of this pole. So what is that? Well, if we are given like an electric dipole, P is just Q over D if it's a physical dipole. So the same will happen for this case. For M is equal to Q over D, so I'll just have that Q is M over delta. So I'll have mu naught m over 4 pi delta r squared. And remembering that our m is again v is equal to j pi over 6 delta cubed, I can substitute that in as well. This will get rid of the pi's as well. So I'll have mu j delta squared over 4 times 6 is 24 times r squared. And one thing I forgot to do, I just realized, is the answer sheet. The answer sheet, this was A4, I think. Did I have even for the previous problem here an answer? Yeah, there I had the answer sheet. So I'll put the answer sheet here as well. So the value is 6.6 meters, and then we had this pi for mu naught j squared over 360 rho g plus delta. And here I think the answer sheet only wanted the formula for b, so we don't have to do any numerical calculations here, which is nice because I find that a bit useless. So now we get to the part B after like 1 hour and a half. This would be like really bad if I was in the Olympiad. Of course, when I'm in the Olympiad, I don't have to talk, but we spent quite a lot of time for only part A. So I'll now drink something and then we continue. Now we assume that in addition to the permanent magnets, we have also plates made from a ferromagnetic material similar to what is used in transformer cores. In the situations we are concerned with, it can be considered to have a constant but very large relative permeability mu r of the order of magnitude of 5 or 10 to the 5. And we are given a hint that large permeability means that magnetic field lines near the outside surface of an object made of the materia are nearly perpendicular to the surface. So this is similar to the behavior of electric field lines near the outside of a conductor. Now we are given a hint which was given here. The induced field to a boundary conditions can always be replaced by some configuration of field sources outside the given boundary, so the uniqueness theorem. And now we are given some boundary condition. So I think we will see some sort of image problem here, where we need to have an image magnet most likely. So let's think. Let's do the problem we have here. So a spherical magnet. A spherical magnet from part A4 is at a distance delta, S is equal to delta, from a thick infinite ferromagnetic plate. The magnetization of the sphere is oriented perpendicular to the plate. Sketch the field lines in the cross-section shown in the answer sheet. In that figure, 3 points are marked. You need to show field lines passing through each of these points in their full length, i.e. as much as fits into the figure. And I have the figure here. So there are other boundary conditions which I happen to remember. I don't know if, and this is funny because I did just yesterday I did because I was practicing for this. I did a Griffiths problem, and that introduced me to a thing I didn't know about, and that is that the field lines have some sort of kind of a refraction law. And how I solve this is through two boundary conditions, because we have a ferromagnetic plate which intrinsically doesn't have any, in this case, it's not magnetized. It has some sort of arrangement of bound currents, but we have boundary conditions that um, the B field perpendicular is, so let's say that this is region 1 and this is region 2. B1 must be the same in the boundary as beneath, and in the same way the H for the parallel must be the same. But H is in this case, because it's just that 1 over mu 1 1 over mu 1 B parallel is equal to 1 over mu 2 B parallel. So and we know that so if we make a little drawing here as well, regions 1 and 2 like this, I know that it has some sort of reflection, so it doesn't really to a magnetic conductor, B should be mu naught I 2 pi r, yes. That is what I did before. But this is not relevant for this. So here I see that the tangent of theta 1 here has to be equal to the perpendicular divided by the parallel. So the perpendicular divided by the parallel, so we have B parallel over B mu, and because of these ones here, and this is also we have this law as well, that the tangent theta squared is B, and when I take when I solve for B parallel here for 1 and for 2, I'll get that this is actually mu 2 B parallel to slash B not parallel, perpendicular to 1, and the same happens there. But actually we notice that all of when I take the ratio of these two, I have mu1 is equal to mu2. So we have a reflection law, basically. So I know that there has to be some kind of reflection. But there's also one thing I know, that the field lines have to be parallel. Not parallel, perpendicular on the outside of the ferromagnet, directly to the outside of the ferromagnet that was given to us. So I'll know that whatever field line here is here, it will go through like this. On the other hand, this will probably have some sort of field line like this. On the other hand, this will go something like this instead, because it's kind of like ferromagnetic materials kind of like suck in these field lines. Then it will have some kind of refraction like this, and then it probably goes to here. And I'll put on these magnetic field lines. So that's 1, that's 2, and then that will go directly here. And then we will have ultimately at some point a really large loop which goes in the same way. It goes like this, then it refracts, and we will have something like this, and it will go outside the figure, but it will come back something like this, I think. And those are the 3 lines we are asked to do. Then, and honestly, I don't have any idea if those are correct. I'm really bad at with like ferromagnetic materials in general, because I've not really dwelled that much into that theory yet. That is one of the things I want to do before the next International Physics Olympiad. That is one of my goals, if I have time alongside school. Um, so now B2. Now the spherical magnet is brought into direct contact with the plate. Which direction is taken by the magnetization vector of the spherical magnet at a stable equilibrium, and what is the normal force between the plate and the magnet? Mark the correct directions with a tick in the corresponding box in the answer sheet. Answer sheet. Incorrect ticks will reduce your score. Okay. So I'll take the answer sheet again here next to this because it is useful. So now I think we have the image problem. This looks like a perfect example of an image problem. Because we are basically, we have a boundary condition that the field lines here must be perpendicular. So let's say that this has any direction like this. Then if I draw like one field line from this, it will have something like this orientation just from this alone. Well, that went a bit too parallel. Let's make like this, something like this, and now this goes like this. But we want the effective to be perpendicular, so this should have a kind of a opposite to here. And how do we get an opposite? That is by making a magnet as far away, and then I think we want it to be in this direction, because then it will have something like this. So we just make the opposite direction, and this satisfies the boundary condition, so this is an actual answer. So this configuration will give the same effective force and the same magnetic lines outside of the ferromagnet. Hello. So now I just have to find out which one of these will actually happen. Um, I think this is the easiest to answer if I'm thinking of torque balance. But and dipoles have a formula for the torque, which is something like the torque is given by like m cross b. And this is not exact. Let's do like this. I don't remember how the signs went, which is a bit bad. But this tells me that when the sign of between these two things is 0, we don't have any torque, and this should give us a balance. So the sign of is 0 when they are parallel. And because this magnet here, or this dipole here, is really close to the, or it's in contact with the ferromagnet, the field lines here are basically parallel, perpendicular to the to the damn, the Finnish accent is unique. Yeah, well, I don't know how much of a Finnish accent I have, but okay. But I have an accent, of course. But where was I? So the field lines here are perpendicular to the ferromagnet. So I want the magnetic or the what do I call it? Dipole to be also perpendicular to the ferromagnet. So we will get these two as answers. And now we just want to find the I like how everyone is removing their messages. Anyways, or chat messages. But then we had a second problem, which was to find out the normal force. Well, the normal force is the same force, so which is how this magnet here. So now I know that it can be something like this. So it's the same as basically. Well, we have two magnets in contact, which dipoles in contact with each other, and they have the spherical magnet from A4, which had like delta, and we already had a force expression which we were using before. 3 over 2 mu naught m squared over pi L fourth. Let's see if I can actually get this this expression here copied over. If I can, because otherwise yes. And now L is again just the delta, and the magnetization again is JV, so I can just mu naught J squared, and V was pi over, so that we have pi squared over 36 delta to the 6th power, because that's squared, over pi delta 4. Then these pi's cancel. Then we have 36 is 3 times 12, so we will have 24, I think, in the denominator. So I will have pi mu naught J squared delta to the 2nd power over 24, like that. Is that correct? I don't know. Hello. Is that correct? I'm just thinking if I have any mistakes in my expression. I don't know if I have. At least I don't see any mistake here immediately. And then we just plug in again our equation or our things. It's 1.5 squared times 0.005 squared over 4 pi, not pi anymore, because those pi's will cancel out, 4 pi 10 to the negative 7 times 24. So we will have a 5.9 millinewtons. Not millinewtons, 5.9 newtons. if you are asking what, oh yeah, if you're asking me what mail I got from IZHO, I didn't participate. And so then I'll just carry over this expression pi over 24 over 24 mu naught j squared tilde squared, and we had 5.9 millinewtons, not millinewtons. Why am I saying millinewtons all the time? I don't know. Then uh, yeah, then now a magnet from part A1 is A1 had those cylindrical magnets, yeah. Okay, US Morad. Okay, fine. Yeah, I wasn't sure because I'm also looking at the chat. Trying to look at this chat because if someone has like a question of why I'm doing something like the way I am, it's useful to have the answer as quick as possible. So it's placed between two thick circular ferromagnetic, so two thick, so I can like just say that they are really thick, and then we have in the middle the small ferromagnet. It had like H and like this. Um, yeah, it's fine. You chat what you want, and uh, because I don't treat it that carefully, so I'll make some mistakes. Anyways, um, so two plates ethics so that the flat faces of the magnets are pressed against the plates and all three disks are coaxial. Find the magnetic force F acting on each plate. Hint, you may neglect the magnetic field both outside the ferromagnetic plates and outside the gap between them. So here we just say there's no field lines, and here we say that the field lines are like negligible. Because they are saying that we can neglect field lines, I have an idea. We can use the method of virtual work to find out. Because this we are saying that only inside there's field lines. I'll use like red to mark the region here. Here are only field lines. So if we start to take these plates away with force F, which is with force F, we will create more field lines, and field lines carry energy. Fields carry energy. The magnetic uh, the magnetic field lines have like, what is it, energy density of 1 over 2 b squared divided by mu naught. Yeah, because the energy density of electric field lines is like this. Yeah. Uh, so I can use that. So now idle the problem is very much reduced because now I just have to find the work done in this specific process to find out the force needed to do that work. And that will find us the magnetic force. So this is the method of virtual work. I think that is the best. So, uh, how will the so we'll have to find and yeah, and of course there will be field lines inside of this as well. How you thought virtual work method? Because we are given that we may neglect both outside the magnetic fields in certain places. That immediately tells me, oh, I can find out the energy relatively easily. And when I know the energy relatively easily, I can also find out the work done relatively easily. And when I can find out the work, I can find out the force using the virtual work method. It is about the problem statement. I am using like the hints given as much as possible. And and what I was saying earlier with the International Physics Olympiad and its structure, the B part had us work with like these magnetic field lines and how they work around ferromagnetic materials. And were given that they are almost parallel, and not parallel, perpendicular near ferromagnetic materials. And we know that this H here is like really, really small. What was the H? Something like 0.002, I don't remember from the part A1. Yeah, 0.002. This is really, really small. And we know that the field lines here have to be parallel. I'll actually draw the field lines with red. Not parallel, perpendicular. And here they are perpendicular. Then there might be something like this, but this is like really, really small. So I can just say that these are in with like good approximation. These field lines, actually, I'll not draw those, are perpendicular all the way, so they are homogeneous. So we have a homogeneous magnetic field outside the magnet, and we have it also inside the magnet. So we have B1 and B2. And to um, find out the energy with this, how do I call it, with these field lines, I also have to know the, yeah, sorry, I was again just thinking something entirely different what I was speaking, and it's difficult to speak. So I have to find out the strength of these magnetic fields to find out the magnetic field density. I think that is pretty obvious. So now I have to find a way to find those. And I have actually no idea how I can do this. I am thinking. Well, okay, hmm. Well, I think I could. Um, I can use the uh, I am not sure. Well, I can actually. Sorry, I can actually. If we remember from A1, because this is actually the thing again. A1 told us something. We can replace this thing, or we can think about the bound currents inside this, and they go around this. We have a current here I, and therefore I can make a loop and use the Ampere's law along like this loop here to find out the sum of these fields. So I can write out, so when we go through this part here, we will have like, and it is important to remember that, yeah, because we are basic. Are we given anything about the magnetic permeability of the magnet? Because we will have to use like the H field. Magnet from A1. Well, I assume that it doesn't have like any noticeable difference. I assume I can just make the loop. Um, uh, I use my loop, and I have like the I inside of it. So then it's only to B1 H plus B2 H over mu naught is equal to I. So I'll have that B1 plus B2 is equal to mu naught I over H. Because the gap in between is the height of the magnet is H as given in part 1. Now I have found the sum. How do I find something else? I need a second equation. Well, I could probably. I could also use the Gauss's law for magnetic fields. If I pick, I'll use now blue. If I pick like something like this, so I'll know that the fluxes, in a way, must add up to 0. Well, that's obvious in the yeah, sorry, not that way, but this way, because I was said that inside the outside the gap, um, the field lines are. What am I saying? There's no logic to what I am saying, and B1 is equal to B2, not necessarily, because we have to take into account the dimensions. Um, they are not necessarily equal, because if we think about this, these lines are connected somehow through this ferromagnet, something like this. So if I say that they go up from here, they must go down from here. So that was related to B1. That was what B1 told us. So I should probably like connect some of these lines so it's more obvious. So it will have some refraction like this. So I'll connect these in some way, not really accurate, but gives us an idea. And the same from the other side, and from the bottom, something like this. And if we take the surface integral, the closed surface integral through that surface outlined, that is a cylindrical surface, b dA must add up to 0. Then let's say that the how I just drew the line, so it goes up from there and goes down from there. Then the flux is positive from B2, and the flux is positive from B2. So I have, because it's homogeneous, I can simplify the integral pretty much. So from the B2, we have the positive part, and then we have the diameter of the magnet, and then we have pi over 4 d squared minus b1 pi over 4 d, the big D given here is equal to 2d, d squared minus d squared is equal to 0. So now I can first of all get rid of this pi over 4's, and d squared is given by like this. So now I can get rid of these d squareds. So I get that b2 is equal to 3b1. So that means that inside the magnet, the magnetic field is 3 times higher. And now I can solve the individual magnetic field, all these B1 and B2. I'll just, sorry, I'll just, yeah, B1 plus 3B1 is minus H, so B1 is equal to mu naught I over 4H. And I was given to us by JH previously. We found out, so we get something like that. And this is the outside, and this is actually this we get something pretty exact here, because this is just 1.5 Teslas over 4. This should be like easily calculatable, so we get exactly this many Teslas. And the second one is just 3 times higher to this. So the inside the magnet we have, I'm just checking that that my notation adds up 1.125 Teslas. So now we have found this. And now we want to separate these. Interesting. Just thinking of what would happen, because now when we change rip these ferromag or rip these sorry, someone DM'd me. So when we separate these things, I'm just thinking, will B2 change or not? Because I'm thinking that this might be not as easy as I was saying with virtual work. But I can still find out the energy, the total energy of this system pretty easily. So actually, let me do that instead, because if I know the work of the of the system, then I know the that the force keeping the system together basically um, is the derivative of that with respect to some sort of um, coordinate system. So uh, just wait, I'm just thinking that everything adds up. What would be the thing we differentiate with respect to? That is. So I'm just thinking we have h. Yeah, we are just increasing the gap in between, of course. So we respect. So that's basically just changing the h in our equations, our previous equations. So, or not in the previous equation. So again, the total energy is the energy of the magnet plus the energy of the field lines of the, or not the field lines, of the field, and the energy of the magnet is minus mb squared. We went through this previously, and um, and b squared. So m the magnetization is j of v of the magnet, and b2 we have as 3 times 4 of mu naught j. So we have minus j squared vm 3 o. Yeah, sorry, I'll write this a little bit more beautifully. 3 over 4 mu naught j squared vm squared, and then we have to add the contribution of the fields. And what do the fields tell us? Well, inside the magnet we have the B2 field, so we have that it's 1 over 2 B2 over mu naught Vm squared plus 1 over 2 of the outside. Actually, I'll just remove this entirely. This part, because it's no longer useful for us, I could add that minus mb2 part back in. I'm just expanding this Vm squared now. So Vm is um, what is it? It's once again it's cylinder. So we have pi over 4 d squared h, and this all squared. We have 4 cubed, and I am too lazy. I am way too lazy to wait a second. No, I'll do this. Because 4 cubed, I never. Oh yeah, 64. I've never really. I only know squares of numbers. Even I haven't even remembered the powers of 2. So 3 over 64. Then we have a pi mu naught d squared h j squared. I think that should be correct. Then the field lines are pretty similar. So from the B2 field, actually let's start with that because that is pretty much identical to this. So that is pi over 4 d squared h, this is the volume, times the volume density of the energy, which is 1 over 2 b2 squared over mu plus, then we have pi over 4 3d squared h 1 over 2 b1 squared over mu naught. And then b1 was 3 times b2. No, b2 was 3 times b1, so we have 9 times b1 squared here. And then we can just add everything here. So we will have 3 plus 9 is 12 times pi over b1 squared d squared h over 8 mu naught. And what was b1? b1 was mu naught j. Mu naught j over what? Mu naught j over 4. Mu naught j over 4. Mu naught j over 4. So we will have mu naught j squared over 4. And actually I can simplify this already. I didn't notice this. 4 times 2 and 4 times 3, this is 2 and this is 3. 3 times 2, no, 3 and 2, I think. Wait a second. What did I just do? Yeah, 3. Yeah, I think that this is correct. 3 and 2. Because 4 times 2 and 4 times. Why am I so getting? Yeah, no, this is 4 times. No. Yeah, yeah, it is. I'm just getting too a bit confused. And then when we get the 4 squared, which is 16, we get 16 times 2, which is 32. 32 is 32 exactly. And now we notice that these are exactly the same expressions, so we get a minus. There's not 12, there's 3. 3 over 32 pi mu naught d squared h j squared. So we will have the force keeping these together is just the minus the derivative of this, which is minus 3 over 32 pi mu naught j squared, and that is d squared. That is d squared and that is j squared. Okay, I am getting confused by my own handwriting, which is pretty deserved because my handwriting is really bad. But yeah, that is our final force, and then we just evaluate it numerically, really quick. I don't remember D anymore. Minus 3 over 32 times pi times, no, times, no, I'll leave that for later, times pi times D. What was D? D was 2 millimeters, 0.02 to the second power plus 1.5 to the second power divided by 4 pi times 10 to the negative 7, and we will have a force that doesn't sound that big at all. Because there's an answer minus. Which problem are we now? We are on problem, what is this? B4, or the last problem of part B, I'm not sure. B3, I think that is. 3 over 32 pi times think of. Yeah, it's 20 millimeters. I looked it whether it was 2 millimeters. Sounded a bit low to my ear, so that is minus approximately 220 newtons. But that is not really the magnitude, that just tells us the direction of the force, as in that it is keeping it together. And so that the problem was to be 1.5 points. Get it a bit smaller. So the formula is pretty simple. It's for the magnitude of the force and 220 newtons. Then we have problem C1 and C2. But let's first read the problem statement of the forward. The magnetic properties of materials are due to the magnetic dipole moments of electrons and atomic nuclei. If the dipole moments orient themselves parallel to each other, the field created by them is magnified. These are ferromagnetic materials. On the other hand, if for each dipole moment there is another anti-parallel dipole moment nearby, the fields cancel out. These are antiferromagnetic materials. In what follows, we consider a very large number of spherical magnets of part A4 arranged at the nodes of a two-dimensional lattice. See real photos of stable equilibrium configurations below. Assume that all the magnetization vectors lie in the plane of the figure. Consider in your calculations only nearest neighbor interactions. Okay. So C1 and C2, and then we are ready with part A, or the theoretical problem 1. And I am not sure if I can, because at least by that problem statement, I think I have no idea what I will be doing. Show the magnetization directions of the magnets in the figure below. You are not required to prove the configuration you suggested is the only possibility. You still need to justify that the configuration you suggested is indeed stable. Find the energy needed to pull one magnet out of this lattice in somewhere in the middle of the lattice. Assuming the other magnets are kept stationary, does the configuration correspond to the order of ferromagnetic or antiferromagnetic material? Hmm. Well, from the previous problem with the chain, we basically got a stable thing when all the things were parallel to each other. So in one chain, actually, I have to get the answer sheet for you, so you know what I'm talking about in a way, because we have to draw the arrows to this one, um, something like that. Um, so if in each, so if we I'm just trying to construct something. So if the things are on these lines, then at least uh, the dipoles are on these lines. Then at least this one row itself is stable. Then we just have to figure out. So if I put everything like this, then we just have to then by symmetry we know that this must also, because this has to be like a replicable thing. This has to be able to this has to be uh, so we have to be able to replicate this 3 by, or this, yeah, 4 by 3 3 by 4 structure infinitely. So by symmetry this second line must agree. So now the only thing is that is this in this direction or in this direction? And now we have to think a bit about the stability. What would be the cause of instability? Source of instability is well, if we think about it, because we were said that let's just look at this. We also said that um, we only have to consider this, and this for stability analysis. So I have to. Well, if I construct the total force or the magnetic field, and look if um, formula energy needed. Yeah, well, it's basically the only thing I can really see as an instability is if there's some sort of torque on anything, and that shouldn't happen right now. So this shouldn't happen if it's still parallel, not like in some, yeah. If the vectors lie on this plane or the yeah on this line, but well then so if we have this like this, and we have the second dipole in either direction, the magnetic field, as told by the very first formula which was given to us, which was something like 4 pi r to the third power 2m parallel minus m perpendicular. Let's check if my formula is correct. Yes, it is. Then let's make a coordinate system right here. Let's make an x and y. And then the magnetic field caused by this here, the topmost magnet, is just one m here because there's no parallel between this line and this one. So this is 0, and this will include the entirety minus x hat. Okay, fine. This indicates that the energy of these to, how do I say this, is like plus minus mu naught. So the interaction energy between these two magnets is this, where plus is if plus will happen, sorry, because W is minus m to the B, and this B already has a minus sign basically. So this will be a negative when they agree on their direction, so they are parallel, and it will be positive if they are anti-parallel. And if I make if I calculate the force on the y direction, which is basically just given by differentiating this force on the second one, hmm. um, well, basically I can just use like common sense, like what I have from uh, from, because negative because I'd expect them to attract when they are anti-parallel like this. The reason is because the opposite ends touch each other in a way. So I'm just trying to find out a physical way to describe this. So if I differentiate this, so is the gradient here, which is basically just 1d dy, and r is basically the y variable. But is it it is positive, so I'd expect it to be something like plus minus, but that would give me the exact opposite of what the intuition says. So I have made a sign error in some part of this. Um, this should be like a easy problem, so I am just thinking of where my approach breaks down. What am I doing wrong? It's minus the gradient. When I differentiate this, I will get the 3 and a negative sign, so the negative signs cancel out. Well, basically, I can just write out that um, these two attract and these two attract, uh, and then because all of these field lines created here are in this line, there won't be any torque, so that will work, and 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 then I just have to find out the. Uh, but I'm just thinking, what am I doing wrong here? I think I'm doing everything correct, but if I'm thinking of that, yeah, this is the problem when the thing falls in mathematics. So I'm just making a sign error in some part, because it will be that it will go opposite to that, and it will be positive when they are parallel and negative when they are anti-parallel. And I want, well, I can, yeah, it might be the thing is that the work I am finding here is with with respect to the topmost. Oh no, no, it's not. I thought but I'll just not care about this right now. I'm thinking about what am I doing right now, because the rest of the problem is pretty much solvable without this, because when these are basically parallel, and they are on the same line. So for these the interaction energy is twice as much as. Well, actually, I can just uh, yeah, or the field created by this by these what do I call these these magnets on the same line is twice as much as the magnets on the same line. But the important thing is that they all add up in this configuration. So I will have that B1 of the total B is, I'll use smaller b for this, so it will be 4 times the b created by one of these rows, which is given there, which is, well, in depends on my um, well, I only care about the magnitude right now. So the b is 4 times the b, which is mu naught m over 4, and these will cancel out. Who will they? Wait a second. I'm sorry about this. I'm just. No, it's not 4 times, is it? It is 1 plus 1 plus 2 plus 2, which is 6. Yeah, sorry. It's 6 times b, which gives us 6 over 4 mu naught. No, this won't work. Mu naught m over 4 pi r. Not r, of course it's not r, because these are still the same magnets, so it's delta uh, cubed. Doesn't really matter, but okay. That is 3 over 2 pi delta cubed. And yeah, I don't see what's wrong with my vector approach. Probably some sign error, but my physical intuition, I think, tells the correct answer. And because I want it to be something like uh, this form, and then I could say that they attract when uh, when we pick this. Ah, it is. Yeah, okay, no, I was just thinking wrong again. Anyways, this is the B, and this will give us uh, and the work needed to pull out something is just a negative of the energy of the system, so that'll give us like B over M, and because we know so much already, I'll just skip a few steps. uh, Delta cubed, and well, I think I can just take the M outside. Have I calculated the M before? Probably. I hope so. If not, I'll have to put everything again. Yeah, I haven't calculated it, so this is the reason why you should like calculate things numerically before, so you don't have to go through the same things all over again in these competitions. But m is pi over 6 delta cubed j. So now we will have 3 pi squared over 36, and 36 divided by 4 is 13, no, 12, of course, and 12 times 2 is 24, so I get that as well away. So 24 mu naught delta third j squared, and actually that, I have a ruler here, and actually it's something like this, and 24. Then I just plug everything in. I over 24 times 0.005, was it? I don't remember anymore. Delta is 0.005, and to the third power times 1.5 to the second power divided by 4 times pi times 10 to the minus 7th power, and we have 0.00, so that's like 29 millijoules. And let's put everything back. 29 millijoules, and that is C1 done. Then we have C2, which is just the same thing but for a different with a different lattice, basically. I am forgetting all of my English while I'm talking. So this one, I really don't want to do this problem. Like if this would be like International Physics Olympiad, I wouldn't do this problem because this looks just annoying. It's doable, but because it's basically the same as this last problem in a way, but you have to just do more analysis and stuff like that, because yeah. 1.2 points is also quite a lot, so this is probably much more difficult. I am from Finland. To the chat. Yeah, nothing personal, but I'm from Finland. Yeah. I'm just thinking of how I should approach this, because I'm not really sure how I can. Because once again, I can definitely say if I want to make everything parallel again, due to symmetry and due to this being a lattice, I can make this. But well, if I think Finsalpi, no, not really. Finland does relatively well in the International Physics Olympiad if you compare to the other Nordic nations, but now, for example, Sweden seems to do much better, and in general, the Nordic people are in the bronze ranks, sometimes silver. For example, Finland has only 2 gold medals thus far. Um, and the thing is, the only reason why I can do these problems is because I knew what these problems were going to be about. I knew that there is going to be magnetism, so I practiced magnetism yesterday. But yeah, I'm not. So if we have like two here, then we have like an equivalent. What is this called? This triangle in Finnish? It's tasasivuinen kolmi. I'll Google it uh, quickly uh, because I was going to say equilateral. Yeah, equilateral triangle it was. Because yeah. So we have this equilateral triangle, and if we think about the symmetry of the situation, um, so we have a field like this, something like this, and then another field like this, and in the intersection point, um, they are going to cancel out in the horizontal direction, but the vertical direction is going to stay. So we only have to, we can say that due to symmetry, um, due to symmetry b uh, bx is 0, and then we only have to think about the no. The thing is that I have it's not about me. I know the terms in for some things in Finnish, but not in English, and I forget terms in either language. In some cases I know the English term, but not the Finnish term. Depends on what where I have learned it from. But yeah, it will only have a y and a y component, this field at this middle point here. So So it will point downwards, that's for certain. And does that tell me anything? Because ultimately, no, no, yes, no. Yeah, I know you were joking, but I was just commenting on it, making myself clear, so to say. But I'm just thinking that because of this pointing downwards, and if I am and it won't have any energy with respect to the with respect to the I just have to make my diagram clear for myself again. So we have a magnetic and we have a magnetic here. One goes there. Yeah, sorry. It will not have bx is 0, it will have by is 0. I was thinking it wrong, because if we have a field line going like this, um, and another from another dipole going like this, they will actually the vectors will be like this, and they will cancel out in the y direction but not in the x direction. I made a silly little mistake there. So now I just can again find the energy, and yeah. So now the B line is mu naught over, and then I have to find this distance. Well, this distance is still like delta, so that is 4 pi delta cubed times 2m minus. And now, sorry, should be parallel. So it is parallel. So now I just have to find the components basically um, to this line, and because it's an equilateral triangle, it's 60 degrees this angle, but the parallel component is I have to connect this like this. The parallel component is going to be um, I didn't get a medal last year because I only started to do physics like in the last academic year. Not the last academic year, but like 2 years ago. I was way underprepared for that competition, but this year I have had more practice. But um, this is not what I want. Sorry, this is not what I want to do. I want to find the x component. Sorry. So when I want to find the x component, then um, the x component is the sorry, I'm getting a bit of a cough here. Um, an x component from the parallel um, part will be a cosine term from the 60 degrees. So I will get a. My cough is getting worse. I should drink something. Cosine of 60 degrees, which is 1 over, which is just square root of 2. Square root of 2 minus the perpendicular component, which so if here is this, and the perpendicular component will be along this line about, and here the 30 degrees will be here, so it's the sine actually. So it's the sine, but once again it doesn't matter. We have this, and actually because we know that in the x that these will necessarily add up to I know I can take a break, but yeah, the cough is just getting a bit worse. Physics is more important than my health. Let's say that. Um, hmm. But it is also important to notice that this will be on the. So if I am thinking of the x component of uh, why am I getting stuck on this? This should be like really easy stuff, but I'm probably due to the way I have now thought of this. So actually, what I want to do, because I know it will be like how do I say this? Uh, the x component in the place I am looking at will be opposite to the dipole vector, I have to just rewrite everything in in with respect to that, and for some reason I am having trouble with that, because if I have the magnetization vector here, then we have the parallel vector somewhat like that, and then I will have the other vector like this. And if I just think about it, the other one is the cosine and the other one is the sine, and um, I was just thinking whether it should be a minus or a plus. That is the only thing I am having trouble with. But if it's a minus, then we will have something like a this one, yeah, cosine minus sine. Yeah, that this should be fine. Okay, fine. And now I just want to write everything back in terms with the the actual m vector, because now this is the x component. Okay, I'm fine. I was just having a brain thought. So now I will revert these back to the with some sort of terms of the um, m vector. So um, now I just go back to the vectors, because both of these vectors are in some way. So for example, the parallel vector will be some k times um, will be a m vector like this, plus something that is perpendicular to this m, which I will um, write with like m, which I will just write with an alpha vector, and that is what I should do. So yeah, I just changed into this coordinate. Yeah, okay, fine. Now I realize what I was doing. Back to business. So now I know that this is still 60 degrees, which means that this is 30 degrees, and this is 30 degrees. So then we will have 60 degrees there and 60 degrees there. Okay, fine. So now the y or the m parallel vector, its m vector component is going to be um, its m vector component is going to be the divided by it's going to be like m vector divided by sine of uh, no, actually, wait, what it's the yeah, it's getting apparently late because I cannot do even simple trigonometry. So sine of 60 degrees is going to be the um, uh, yeah, of course, that's cosine of 60. Cosine of 60 degrees is going to be m by the m parallel. So I know that the m parallel can be written with cosine 60, which is root 1 over root 2. So like this, plus a plus, yeah, plus m plus the alpha vector to squared, and the m parallel will look quite the same, but just like this, unless I am mistaken, which is probably the case. Yeah, I think that should the key word being should be the case. So we have two time. So we have so we will have times root 2, so I will have m vector plus alpha vector minus. But what? I swear that I did like a similar problem yesterday that had this like that same kind of like switching vectors around, but still, for some reason right now I am having trouble with this. So actually, uh, I think this should be quite similar to the first part. So I'll skip this part for now, and I'll come back to this if I have time, because I have spent way too much time on part A. And this is going to be just the same thing. So I'll just express my approach to this. Basically, it's to again calculate the energy, and in this case, uh, we are interested in whether the returning force will be when these are all in this direction or anti-parallel. And how can I do that is to find out when we have like three balls like this or magnets like this, is to find out the resultant magnetic field from these two things, which we know from symmetry must be here in the x direction. And then I calculate the energy, and by um, adding all the other energies from all around and keeping mind of the signs and doing no sign like, how do I say this? I by no by looking at the energy given by these two, the interaction energy, and then differentiating it, we should get the expression for the force, and then we just pick the sign which gives us the return, which gives us a force that keeps it stable. And then I will know if it's a parallel or anti-parallel. My intuition is that it's parallel, but I don't want to do this. It's just a mess. I will come back to this later if I have time, because yeah, I've already done like 3 hours of part A. And it's probably more interesting for people to see the other problems as well. And because because like if I don't write like anything, um, like the sine 60 degrees out, like as 1 over square root of 2, and just take a sine alpha. I think the bx component, because I just did like yesterday something really similar, which had like this exactly the thing that we first um, take the projections and then we switch the vectors around. And I got something from the vectors that looked like cosine squared alpha minus 1. And this is what I'm pretty sure this should give us. But I am not sure where I am going wrong. Uh, so I don't want to Uh, the problem is that I'm having hard time to thinking about the science right now, because that gives us a cosine alpha in the x direction, and in the y direction it's not, or in the parallel direction it's like the cosine term, that then in the perpendicular term it's the sine, and then when we because then these should cancel out when I take notice of the basically the alpha vector should cancel out, and I'm not sure why they don't cancel out, because right now I would get something where it's going to stay the same, the exact same. And well, if I just this is always really hard for me to do, is to give up, so I just want to make a one last try. So m parallel, uh, which is given by that vector there, um, it is written with m cosine alpha and plus the alpha vector, or is it? It's not given like that, it's given like this, I think. Okay. So if we have the parallel vector here, and then we have the vector, the magnet dipole vector like this, and then we have perpendicular vector to that. Basically, these two have to add up in some way to this, and here we have a 60-degree angle, so we have that the uh, that's cosine, and then it should be uh, sine, and for the perpendicular vector which goes around here, it should be like pretty much the same. Um, but this is the problem that I'm having, that this is a bit too. No, no, no. Actually, this looks somewhat correct. And if I would substitute these back to the original, I would have like uh, m parallel is times cosine, so I have like an yeah, it's weird what I'm doing right now. So I just skip this problem and come back to it. And when I have this would be what I would do in the actual competition. When I get stuck, it's bad to it's bad to just try and try and try. If you're stuck, you should do something new. Use your time otherwise. This should be like simple mathematics, I know, but for some reason I'm having trouble with this right now. So I'm going to go to the James Webb Telescope. This is quite a big problem. This will take a lot of time. So instead of that, I will do the third problem, which is pretty short. and then I will look how much time I have, and then probably to do the second problem. So scaling laws. Scaling laws describe the functional relationship between two physical quantities that scale with each other over a significant interval. This functional relationship can be a power law, but there are other possibilities too. Oftentimes, exact expressions are beyond reach, but scaling laws can be still derived. A spaghetto straw of diameter d is being balanced horizontally from its middle. If d is equal to 1 millimeter, the straw breaks under its own weight once its length reaches L is equal to 50 centimeters. What is the maximum length L of the straw of diameter of 1 centimeter? And this is actually somewhat of a classic problem, but the thing is that why does this break? It's due to stress in the spaghetto straw. So we will have to analyze the stress a bit. But if I just split this in two and just look at the right side, for example, and take a torque analysis, then I'll see that the torque is somehow related to the well, it's the torque from the gravity is balanced out by the torque from the stress forces. And the idea is that I can look at how the gravity and the stress forces are proportional to the torque. So this is the approach, and why I know this is I've done a similar problem before, I don't remember where, so this is in a way quite a classic problem. So yeah, and also this third task is pretty uncommon for for what is this? The International Physics Olympiad, because usually the problems are more like the problems I've done here, so that they have many subparts and they lead you into the right way to approach. This leaves it completely open. So, so that's a bit untypical, but yeah. So the torque from the gravity is of course proportional to the mass because it's the gravity, and then it's somehow related to the length, to the distance of the center of mass. But that center of mass is just proportional of the right hand side, of course, is proportional to the length of the thing. So we have this proportionality, and the mass, if we have some density, constant density for this, then the mass is related to the diameter squared, because and that gives us the area and the length. So we know that the mass is proportional to d squared L in some way. So we just have d squared L squared, and then what we know about stress forces is that they are proportional to the stress. Well, duh. Of course, it is proportional to a what I was thinking about, like the because stress is defined as the some force over a basically a pressure type of like thing. So in this case, of course, the force is proportional to the stress itself. And as I was saying, we have that F is equal to sigma A, and A is proportional to d squared. So we know this. So now the torque from the stress is proportional to F. And because the stress basically No, we have to still find like the distance. How do the um, how does the length the I'm trying to find a proportionality to the moment arm basically. What happens to the moment arm? How is that related to the so the stress is uh, what basically we are trying to find affects like in this direction. So of that should be proportional to d, so their thickness. So that gives us a proportionality of 6 sigma d cubed. And now I know that of course the torque is proportional to the torque, so I will have that d squared L squared is proportional to the sigma um, d squared, but that is just not necessary for us at all. So we get this proportionality to d cubed, and that gives us ultimately that L squared is proportional to d. Um, and because we wanted to find the maximal length, now we just have that L squared, L prime squared over L squared is equal to d prime over d. So L prime is equal to L over d prime d squared. And now we can just plug in the 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 values given to us 1 millimeter, 50 and 1 centimeter. So that is 0.50 meters over 0.00 no 0.01 meters and 0.001 meters. And yeah, this is basically, you could calculate this in your head because I am too tired to do anything right now, so I'll just do it like uh, you wouldn't, because you get a square root, but 1 meter 58, 1 meter 58, yeah. 1 meter 6, yeah, let's use that instead. So I'll take the answer sheet. I have lost my answer sheet. Oh, it's there. Um, well, actually, that's unnecessary. It only has one thing, basically. Then we have B1 sandcastle. This is one of the problems that I have thought the most before, because I was really interested by this last problem set. So this is a thing I have thought a lot about, and what is the physics. And I really like this last problem because it really forces you to think about the physics that's going on. So um, so here we have the average grain volume of coarse grain sand is 10 times as large as that of fine grain sand. Wet fine grain sand and wet coarse grain sand have both optimal water content, i.e. assuming the maximal strength of the constructions from it. and are used to build two cylinders of exactly the same shape and size. The strength of each cylinder is tested by pressing it between the two parallel plates. Um, um, the cylinder made of coarse-grained sand gets destroyed once the force applied to press the plates reaches 10 newtons. How large is the force needed to destroy the cylinder made of fine-grained sand? You may ignore the effects of gravity. Well, there are few things. Yeah. So, what is keeping this sand together? That has to be related to the sorry water somehow. And how does water? So I'll make a grain of sand here and another grain of sand here, and there's water in between these two. And how does this water keep these two together? There's two processes going on with both are related to surface tension. Of course, there's the actual surface tension force, which keeps it together. So that is in some way, or yeah, the force is given by this. So that is really so it's proportional to the how much like contact size we have with the grain, and that is proportional to the actual physical size of the grain. So we have some characteristic radius, characteristic length for that, which is just actually it's more better to work with this and yeah. And then there's the capillary pressure in these parts basically, the tension, the pressure being different and basically pulling it them together, and the capillary pressure difference, the difference is proportional to the radius of this curvature here, and 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 yeah, that is of something like this, where sigma is again the surface tension coefficient and rho is the radius of curvature in some way. And I'm just and basically this radius of curvature is of the same, is proportional in a way to the grain size itself. So we have this. And if we think about the force caused by this pressure, that is just pressure times area. And the area is related to, is proportional to r squared. So we actually have pressure over area is sigma r squared is equal to sigma r. And we see that these are basically the same order of magnitude. They are the thing keeping this thing together is in any way sigma r. The thing we have to do is to analyze both of these processes because at least my intuition doesn't tell me which one must be larger, or if they are of the same order of magnitude. So I had to make this analysis first. This is what I have been thinking about for like 4 weeks now, and now I can finally write it down. And now we have to think about how will when will it break this cylinder of sand, and um, the thing is that we can just immediately say that the um, we can immediately how can I say this? I have to think. Actually, I'm not. I think I found a mistake in my like thought process a few weeks ago. So I'm I am thinking. Well, basically, I think the capillary pressure here is the better way to approach this, because we just have to. The pressure keeping the sand together must be overcome, and because we have two cylinders of sand, basically, this we just have to apply some pressure that is equal to the pressure of the capillary pressure, and because for both cylinders um, for the fine coarse sand and the not fine coarse, fine grained sand and coarse grained sand is the same. The dimensions are the same macroscopically, so we just have to apply a pressure that is much higher than the uh, capillary pressure. Not much higher. We have to just break the capillary pressure, and then it will collapse. And that force is applied into the same area on both. So the force has to scale with the capillary pressure. So we get that the force to break the things have to be proportional to the capillary pressure, which is proportional to 1 over r, which is proportional to the volume cubically. So we get that it's 1 over cube root of v. And now I can just make we know that the f over f c is equal to cube root of v c vf, and we know that the fine cost or the coarse grained sand has the volume of 10 times higher, so we just have a 10 here. And and wait, yeah. So yeah, and then we have FC 10 is equal to 10 newtons times the cube root of 10 is 22 newtons. Nice. This problem seemed really interesting to me, but and also pretty difficult. Interesting. So the spaceship of an interstellar expedition travels at a constant magnitude of the proper acceleration g is equal to 10 meters squared. No, 10 meters per second squared. I.e., this is the acceleration of the spaceship in the inertial frame of reference where it is instantaneously at rest. The passengers must be able to return to Earth within their remaining expected lifetime of 50 years. The maximum distance from Earth reached by the spaceship is d. If the acceleration is increased to g prime is equal to 15 meters per second squared, the spaceship can reach a farther distance d prime. What is the ratio d prime to d? You may wish to use the relativistic addition formula, however there are also other approaches. You may need to deal with hyperbolic functions defined as follows. Depending on your approach, you may need one or more of these integrals. Well, for me the key here is the hint given the relativistic addition formula. Because if we think, we all have a well, first of all, let's analyze what happens inside this frame of reference of the rocket ship. For them, it is almost like, in a way, it's like traditional kinematics. They have to, for a let's say here's the remaining life expectancy is 50 years, so let's set the time to be 50 years, so the period they go and they come back. Then they accelerate at the quarter of t uh, of the way, and then they start to decelerate. Then when they stop, they start to accelerate back, and then they decelerate. And now we can analyze this thing from the lab frame. So here is the Earth. And here is the distance what they are going through, but that doesn't really matter. And there, here, somewhere there, there's the rocket ship going at some velocity v. And in relativity, it is usually really useful to work with the what is it called? I don't. There's a fancy name for this. For this uh, factor. I think it's like, no, I don't remember. Basically, it's usually denoted as beta and c. So if we have a velocity v, we just have the, oh, this is getting a bit laggy. So what I'll actually to do now, this happens when the whiteboard has too many elements. So what I'll do now is take this with me and then um, go home and a new whiteboard, because let's see if no, it doesn't want. Oh, it had it in mind. So is to say that the v is equal to some beta c. That is pretty common in relativity. Why beta? I don't know. Yeah, it could be anything else. And I think it's useful to use that. And we had that these are equal to 50 years, which is the and the quarters is the time period, which is pretty much relevant for this problem. And they are accelerating, and here we are in the lab frame, and here they are going with some velocity v. And we are interested in what will happen in some short time dt. Well, it will have a new velocity v plus dv. And how can we calculate this new velocity is through the relativistic velocity addition formula. And this is the thing I always forget the signs of, but because in the we can go to the frame which moves at the same speed as the rocket at some period of time, and then look at a period of t tau, where tau is the proper time of the spaceship, and in that time, in that frame, we will have a non-relativistic acceleration, basically, or because the acceleration is so small, there won't be any relativistic effects in this frame, which is going pretty quick. So the new speed in this frame, let's use v prime for the speed in this frame, will be just the new speed will be just g d tau, g d tau. And now when we go back to our lap frame, we just have the speed of the frame from which we are coming from, which we have given to be as v, plus the speed of the what is this? The um, the the speed of the rocket ship in the new speed of the rocket ship in this frame of reference, which is g d tau. And now we will see why it's convenient to work with the then over 1 plus the speed of the frame, then the new speed over c squared. Now we will see why it's convenient to work with beta here. It reduces things and makes things more symmetric. Because now when we divide everything by c, and do the change v is equal to beta c down here, we will get that beta plus d beta is equal to beta plus g d tau over c divided by 1 plus beta g d tau c. So this is pretty symmetric. And because we are talking about differential elements here, d tau, basically infinitesimal elements, or elements that have infinitesimal size, or magnitude in this case, we can use the first order Taylor polynomial with respect to d tau here to get an exact simplified form for this. So what does the Taylor polynomial tell us? Well, the Taylor polynomial of the first degree centered at 0, so the Maclaurin polynomial with respect to x0 is just a function at 0 plus the derivative of the function at 0 times x. And what is the 0 of d tau? When d tau is exactly 0, what will we have? We will have exactly beta. Then we will have the derivative. Well, the derivative is, in this case, we have to use the quotient rule. The numerator has a derivative of just g over c. G over c. And that must be multiplied by the denominator, but because we are evaluating this derivative at 0, we can do that immediately, and we see that the denominator is exactly 1, so that's nice. And then we take away the so we take the derivative of the denominator now, which gives us beta gamma over c times the numerator evaluated at 0, which is just beta, so we get beta squared, times d tau, which is our x, basically. So now I can simplify things a little bit. First of all, these betas cancel out, so we have d beta, and then I can take gc as a common factor, g over c 1 minus beta squared d tau, and now we just have a differential equation. So now we get the, which is separable, 1 minus d beta squared gc d tau, and when we integrate these, this integral was given to us, that's the arcus hyperbolic tangent function. So we get a tang 1 minus beta squared basically is equal to gc tau. And do I have the arc tangent? Arc. Yeah, it doesn't have that function. I'm just trying to think when will actually, yeah, I can just check. Arc, no, tang of 1 of 0 is, yeah, okay, fine. So now we will just have sorry, when we, I should make it a bit more clearer what I'm doing right now. I'm basically integrating this from 0 to a new beta. Well, I should probably put primes on these so it's more clearer that they are different variables, yeah, and from 0 to tau. And now I just noticed that we get an minus how does this integral work exactly? That's what I'm just thinking. Oh yeah, oh, of course, it's not arc. Yeah, sorry. We just have the arctangent of beta that was already given to us. I was just messing about apparently, and uh, the hyperbolic tangent of 0 is 0. That is given by the definition, which is something like this. And if you see when we put 0 here, um, uh, this numerator goes to 0. So that's why. So in the same way we get that 0. So we immediately get this out. And this gives us an expression for beta with respect to proper time. That is important, proper time, because now we can find out the half of the distance, because half of the distance is used for acceleration. So we know that the half of the distance is just some sort of integral of pounds this is in the lab frame again. So we are in the lab frame, the rocket ship is going at v, which is a function of t. So we can just use the normal kinematics. But now we know that v is beta c, so we can take the c out and have beta dt. And this has some bounds a and b, which we don't really know yet because the proper time is not the same as the lab frame time. So we will have to use the time dilation formula for the differential element to evaluate this integral, and then we know the bounds suddenly, because in the proper time they are only accelerating quarter of the time. So AB is equal to tan GC tau dt. So now we have to think about the time dilation. Well, time dilation formula is just gamma tau here. So dt is equal to gamma d tau, and gamma is actually, and here again we see why exactly the um, why exactly data is such a good variable to have, because Dante, the is I think this is called the Lorentz factor, is given exactly as 1 minus beta squared. So this makes our life so much easier. And if we uh, put our uh, b squared here, which is tang, so we get 1 minus tang squared of something, which I will say just x. Now we can use some trigonometric identities, basically, I think. Well, actually, we don't have to do that because hyperbolic functions are actually much easier than trigonometric functions. We'll just use the... oh, is it given? Is it given? Is it given? No, it's not given, so we have to use the... definition here. X minus e minus x ex plus minus, wait, plus e minus x, like this, and all squared. And I don't have any more space, but that doesn't matter, because now we will have 1 minus e x e2 sorry, e2x minus the ex times e minus x, which is just 1, plus uh, e minus x, yeah, plus e minus 2x, I think. And then we have basically the same here, but with plus 1, and all over this. Then we just subtract. Wait a second. I am going to have to check something and drink water. But sorry. I'm just checking that I'm doing everything correct again, because I feel like this is not going to simplify in the way I wanted it to. Because the denominator should be something. Because I know the answer of this, I'm just showing it to everyone. Because not everyone is familiar with hyperbolic functions. Um, uh, so we have, say, so yeah, it should be correct. So we have this expression minus that expression all over 2, which gives us like, why isn't this giving me what I want? That is the question I'm having. Uh, uh, I have probably made a mistake, or then I'm just thinking it too much. Because when I simplify this, we get 2x, so these cancel out, plus 1. So we get 2, and am I doing a mistake here? How do I get good at solving problems? I'm not good at solving problems, as you can see. I'm getting so stuck on the simple things, at least the math right now, even though I have done this before, like 100 times before, and that's getting annoying to me right now. Oh yeah, actually, I made already one mistake. This should be 2, first of all. 2. The thing is, what I'm expecting to have. Well, yeah, let's just do it like this. So when we simplify this, we will have we will have e, we will have like 2 over. No, we won't have 2. Oh yeah, now I see it. Yeah, I forgot. I forgot how the hyperbolic cosine was defined, even though it's given here. Um, 1 by 2. So we will have e to the to e to the x plus e to the minus x squared. So this is exactly e to the x plus e to the minus x divided by 2, which is the hyperbolic cosine. So when we simplify this expression here, we actually get that the dt was gamma. Oh, sorry, we get that the gamma is the hyperbolic tangent of beta. And this is also the reason why people want to work with beta, because then beta can simply, so not hyperbolic tangent, hyperbolic cosine, as I just said. Hyperbolic cosine, did I write? Yeah. Hyperbolic cosine is hyperbolic cosine. Beta. Sorry, I was getting ahead of myself. Uh, I was mixing up two concepts. The thing is that yeah, we already found out that beta is at the tang that beta is tang g tau c or something like this. This is called the and this is called the rapidity. This basically, if I remember correctly, I was just getting ahead of myself. Um, so yeah, we will get whatever is here as x, and we know what we have as x because that was that g tau c which we found previously. So we get that gamma is the hyperbolic cosine of g tau c. Yeah, I was just getting ahead of myself a bit too much, trying to be trying to find connections in places where there are no connections, or there are, but mixing up things in my head. So now we know what the Lorentz factor is. Then it is really easy to write out this as the tau. So now we will have that this integral will become from 0 to t over 4, because we know that this bound must hold. This is what we define it as. Tan hyperbolic tangent of g over c tau times the hyperbolic cosine of g over c tau d tau. And now we also know that this is equal to the hyperbolic sine. It is exactly the same thing with with how do I call this? The normal trigonometric functions, the circular trigonometric functions. And now we just have to perform this integral, but we don't have to. We are given that. So we know that this is going to be c over the hyperbolic sine, I think. Yeah, that's 0 at 0. So then we will have just the hyperbolic cosine of g c g over 4 c t. But not exactly. Not exactly. Because um, because yeah, of course this doesn't hold like this. Of course, I'm getting tired, as you can see. We have g tau over c. So we will have the a factor of c2 over g of and the sine will become a hyperbolic cosine, so that is 0, so that will give us 1, so we will have 1 over this minus 1. And now we know that this is equal, so now we can solve for d. D is equal to 2c squared over g, uh, or actually more like we can now say that d is proportional to the hyperbolic cosine tau minus 1. And now we will note that d, was it d prime, that was used as d prime over d, is cosine, yeah, the cos of g prime c tau minus 1 over cos of g over c over, I think. Not exactly. We forgot already the 4 over c here. So now, what were we given? Um, yeah, I forgot. Of course, he has also g. So we will have a prefactor of g and g prime like this. So then we will have something like I think we have 50 years. So I'll just write everything again. So we have 10 times the cosine of g prime, which is 15, over 4 times 3 times 10 to the 8 or something like that, times, what was it, 50 years, I think, was given. Yeah, 50 years. So 50 years is 50 times 365 times 24 times 60 times 60 minus 1 divided by 15 times the cosine of uh, 10 times 4 times 3 times 10 to the 8th power times 50 minus 1. Not 50, I forgot the whole thing with 365 times 24 times 60 times 60, and we get something like 480. Nice. Inked somewhere. So now we have the last problem, and this was actually quite weird to see because in a way this is well, actually I should read the problem. This was weird to see because I was actually one time in our I saw an article about the uh, buoyancy of spheres and how that how that introduces like a solvable cubic to physics because it's solvable balance situation, and this is related to that a little bit, not really. A solid wooden ball of radius r0 is floating in the water. Ignoring frictional effects, the frequency of small oscillations would be omega naught. But because of viscous friction, after being displaced vertically, the frequency of decaying oscillations is actually 0.99 omega naught. What is the minimum radius mean of a wooden ball floating in water that undergoes small oscillations when displaced? Hint: the viscous drag force acting on a given body is proportional to its speed relative to the bulk of the fluid and to the viscosity of the fluid it's moving in. So, let's think about the forces that are affecting it. Well, then, of course, the buoyant force is going to give us the driving force behind this oscillation. And we know that it is proportional. So let's say the restoring force, the driving force, is proportional to the dimensions of the sphere and to the depth of the sphere. So let's say that x naught is the so that we have a sphere on water. So the middle point will be x is equal to 0, i.e. where it would be at in equilibrium. So then the positive direction doesn't really matter, but then it's proportional to also the um, is uh, when it oscillates, it will go down and under. So basically, it will some way be proportional to um, the how can I say this? Basically, the oscillations depend or the amount of so if we just look at small oscillations here, um, the cylinder the segments of this sphere will be almost like cylinders because of the curvature being rather small with respect to the amplitude. So we will have so the volume of the displaced liquid water is proportional to this, basically. Um, then we have the viscous force, um, which is, of course, if we think about this logically, it is dependent on the size of the object. The larger the object, the larger the viscous force is. Then we have been given that it's proportional to the speed and the viscosity. So we know that it is proportional. The viscous force is proportional to eta to the alpha and v to the beta and r to the gamma. And now we have to do some dimensional analysis. Force has the dimensions of the mass and mass length over time squared. So we have mass, length, and time minus squared. Then the viscosity is given the units. It is mass over kilograms over meters per second. So this will have -1. And these will all have the term of alpha, actually. I forgot we are doing a dimensional analysis here. Times the one from the speed is meters per second, so it's length over so we will have plus beta minus beta, and then we have the size of the object, which is meters, so we will have plus gamma. So now we immediately see that alpha must be equal to 1. Then t is equal to -2, so beta must be equal to 1. And then we have minus alpha plus beta is equal to 0. and that leaves that gamma must be 1. So we will have that the viscous force is proportional to eta VR. And why I'm doing this is because we know we have a dampened oscillation. I'm trying to find the equation of motion uh, to this. Because the equation of motion gives us the actual, how can I say this, the actual uh, periods or the frequency of decaying oscillations and stuff like that. So that is what I'm trying to find. This is basically just because it is just looking at the solution for a second order linear differential equation, basically. So, and now we still have to think about the mass, but the mass is only proportional to the volume of this sphere, which is proportional to r squared. So now we know that the equations of motions usually look something like mx double dot plus a gamma, not really gamma, bx dot plus some cx, and where b is related to the opposing force, which is the viscous force, and the restoring force is related to c. So now I can just put the proportionalities here and just give them some constants. Constants. So we have a k 1 r cubed x double dot um, yeah, exactly, k1 x double dot plus k2, no, it's not, m, no, r cubed x double dot plus k2, what did we have, eta vr, eta vr. Ah, yeah. No. This doesn't make sense. Uh, this is exactly what I wanted us to have, basically. But we are only interested in the so it's basically just k2 r x dot, because v is equal to x dot, so we have r x dot, basically. That is what I wanted to have. I just realized that I got something completely nonsensical. And then I have the third proportionality constant, not the, yeah, okay, not proportionality, but the constant. And then we have the driving force, which was r squared x is equal to 0. Then we can divide by k1 r cubed. So we will get x double dot plus k2 over r squared x dot plus, not k2 times r squared, but k2 over k1 r squared x dot plus k3 k1 r x. And now we know the solution for this type of an equation. It is minus gamma to the fourth, where this is the gamma term and this is omega 0. And this is actually the same omega 0 which we have here, because that is respective of the um, of the um, of the well, that is the angular frequency you get if you um, get rid of this term entirely and you have like normal harmonic oscillations. Not gamma over 4. Wait. So anyways, we want to solve this differential equation. This is one of the few formulas I remember, because this is so, yeah, this is really, I use this a lot. I've done a lot of oscillations recently. This is why I love this problem. At least I've had fun with it. So that is there's no 4 there. So that is why I remember this equation. It probably is useful to know by heart when doing oscillations and t there. So now we know what omega naught is, and we know what minus gamma is, and we know how they are related. And also the thing is that this oscillation will only happen when wait, what we were asked is when does the um, when does the sorry when does the oscillation happen? What is the minimum? What is the minimum um, radius? And this second order differential equation will only have a oscillatory solution when it is underdamped. And underdamped, and this relates to the discriminant of this. I don't remember the name, but the um, characteristic equation. Yeah, when the when the discriminant of the characteristic equation is um, is um, is 0, and this will basically just mean that the you can actually see it from this equation that the critical point will happen when this is equal to this. You get it by looking at the discriminant of this characteristic equation, but basically that just for me means that omega naught must be equal to um, gamma at the critical point when R min is present, and then we just take um, the respective equations from here, and then we notice that k1s cancel out, and wait a second. No. Yeah, this should work. I'm just pretty sure that I have made a mistake. Because I'm fairly certain of my my k1 has been subtracted. Yeah, r cubed is equal to I'm sorry. Because yeah, this has this form. Wait. I'm getting confused. Um, I had like a clear idea in my head, but I lost it. So that is what I because right now I'm a bit stuck on what to do next. Um, it is almost done. I know. I just for some reason I have to recollect my thoughts. Recollect my thoughts. The thing is that I made a little mistake here, and it's good that I noticed because um, this is 2 gamma. The equation is by tradition is written like this. So it's a 2 gamma. So actually gamma is k over 2k1 r squared. So yeah. And actually now I know what to do next because we need just a second equation. That's the trick basically. And this is omega not squared because this is how it's usually written. Yeah, sorry. I I got a bit too excited for a while because I realized how to do this, and I'm really happy that I have done so many oscillation problems lately, so that this felt rather feels felt like a fun problem, a rather easy problem actually. Anyways, so now we know that the Armin requires that um, Armin requires that omega naught is equal to gamma, and this creates us that k. What do we have? K3 over k. Actually, yeah, it's easier to do like this. K3 over k1r is equal to k square, k2 squared, 4k1 squared, and min 4. And now we have the actual equation. Uh, so now this r min goes, this becomes a 3, this k1 goes, this disappears, and then we have that r min cubed is equal to k2 squared over 4k1 k cubed. And now we have the last piece of information which was given to us, that omega is 0.99 omega naught. And we know what omega is. We can actually um, um, square this on both sides to make this easier. So that's like, no, well, I'll just leave it like omega squared 0.99 squared omega 0 squared. And this will give us omega 0 squared minus gamma squared. And then we solve for uh, sorry, what is the minimum uh, That is at R0. What is the minimum? Okay, okay, so yeah, fine. Um, then we will have an R0. Wait a second, I'm thinking again. If we look at this K2 over K1, K3, this is now just algebra, basically, manipulating things. If we put omega 0 naught and gamma squared, um, yeah, you see, I've done this for so long now that my brains are starting, or not so long, too late now. It's like that my brains are starting to not to stop functioning, and so omega 0 squared is well, actually, if I just divide everything by omega 0 squared, I will get an easier equation to solve, because not easy equation to solve, but easy equation to manipulate, because we want this arm min uh, some way or form back into the game. And when we do this, this is 1 minus gamma squared, which is k2 squared over 4 times k1 squared r not in this case, not fourth divided by k3 divided by k1 r naught. Well, first of all, um, we will have an we will have an uh, 1 minus k to the squared 4k1 k3 r0 cubed, and no, yes, no, wait, this is exactly the form of that, but I'm just getting the feeling that something right now is not because the dimensions don't match up, so I am checking where I made this small little error. K3, K1 are not oh yeah, I didn't make any mistake. I just got ahead of myself. Is equal to 0.992, and this is just the same as 1 minus r min r naught cubed is equal to 0.99 squared. So now we have that 1 minus Okay. And then we take the square root, the cube root of this as well. Yes. So we have like 27.27. So we have R min is R 0.27 R naught. And that should be the last problem done. And then we can go to the second problem, which is quite massive. And with the second problem, I'm going to do it like where I am going to. I'm still annoyed by this last problem because for some reason I just cannot think it straight through, and that's a bit embarrassing doing this live that I mess up with because of the most simplest of vector calculations. So that's not that nice. I don't see where I am going wrong, but that's not. That's sometimes life. Sometimes things happen this way, and that's not anymore interesting for you guys to look at because the idea is exactly the same as the problem before. But yeah, then the James Webb Telescope. This is a question on the physics of the James Webb Space Telescope. Light from a star strikes the primary mirror with an area of 25 meters squared. Um, and reflects off above. Sorry. Yeah, and reflects off of a secondary mirror. The focal length of the system is 130 meters. The light is focused into the ISIM, which contains the CCD cameras. The nearest red giant is, I'll just take it here. The nearest red giant is 89 light years distant, has a temperature of D star 3600 Kelvin and a diameter of D naught. Calculate the diameter of the focused image of the star on the CCD camera imaging surface. Actually, we are working with a bit too large. This is better. Um, Diameter of the focused image. Well, this is just like a geometric. Um, so we basically have like uh, two mirrors, and it is also important to note that um, I'll actually take that the focus is 130 meters and the star is really far away, so we can say that uh, the 89 light years of distance is probably like very much larger than the focus, not this way around. Uh, uh, um, Wait, I need to. Sorry. Um, so the distance of the nearest yeah, my brain is stopping all its functions right now, but I'll just try to push through. So we have let the distance of the star be like a big D. So then we just have the because the focus is so so much smaller, we can basically say that D is infinitely far away. So that means that the image will form at the focus. Which means that and the magnification of a mirror is basically uh, given by the of a spherical mirror is given by like the distance to the image per the distance to the object, which is in this case is like f over d, and that is then just that the image di over d naught, no, di is equal to f over d 0, and that is given, and that is basically 130 130 divided by what was 89 light years. So 89 light years is the distance light travels in 89 years, and the distance is just so 89 years is 365 times 24 times 600 times the speed of light is 3 times 10 to the 8 about, and times 1.7 times 10 to the 11th, and that gives us 2.6 10 to the negative 5, which is basically just the same as 26 micrometers. Hmm. My coffee's getting a bit wet. Yeah, speaking this much is not really good for your cough when you have been sick for quite a while, but as said, my health is secondary to physics, so a numerical value is 26 micrometers. Nice. Then, second problem. Estimate the diameter of diffraction central maximum on the CCD imaging surface. Um, uh, Assume a wavelength of lambda 800 newtons. Well, this relates to, I don't remember what it's called, but it's basically like the circular diffraction, because the large mirror is our like aperture. I don't remember what it's aperture basically, through which the diffraction happens. So we can um, say that the angular radius of the central maximum must be 1.22. This is one of the things you really have to remember for physics Olympiads. They rarely ask the other maximums, and I don't remember them. But then this central maximum for the circular diffraction is it's pretty difficult. It's really lengthy to derive. I once looked at it, and it was difficult for me, at least back then. So, and then we need the size of the um, uh, basically, I think it's the diameter. So let's say diameter. Well, I already used big D. Let's use delta. Um, Delta and lambda is given, and the and we know that the area is pi over 4 delta squared, and that means that delta is something like square root of 4a over pi, and the angular radius gives us a diameter for the what is the symbol used in the answer sheet? It's d diff. Yeah. So it's pretty much so we have the mirror here where the diffraction happens, and basically here we have the secondary mirror which refracts it once again. But this creates the image, so this doesn't really create any more diffraction to this. So the only thing really what matters is the angular diffraction here. And the image is formed at the focus. This should be at the focus. So we get that it is 2 times, we know this theta, theta tangent theta is at d diff over the focus, so we get 2 times the focus times the tangent of theta, and if we think about it, this is like in 800 nanometers, and this is in like meters at least, so theta will be much smaller than 1, so we can just say that this is equal to this. So then we have 2.44 f over lambda over 4a over pi, and this was 2.44. The focus I already know, it was 130 times the 800 times 10 to the negative 9 divided by square root of 4 times 25 meters squared divided by pi gives us 45 micrometers. Although I think at this like scale, like 1.22, and because if we think about the normal diffraction laws, this theta would just disappear. It would be L over delta. I don't know if they accept not using the circular diffraction, but that could also work. It's not that the magnitude, the order of magnitude works, basically. That's what I'm saying. And here we are doing quite a lot of approximations. The diffraction is all about approximating, basically. Well, if the CCD is not cooled and can only lose heat only by radiating from the top of the imaging surface, what would be the equilibrium temperature of the CCD at the location of the image of this red star? Assume that the CCD surface is a black body, provide a formula and a numerical estimate. Well, first of all, we care about the The stars also can be approximated as a black body. They radiate with the red star, or maybe just S for star, radiates um, with like 4 pi r of the star squared sigma, which is the Boltzmann constant, no, Stefan Boltzmann constant, T S of the star. Okay, fine. And because we are so far away, this circular or this spherical shell of like radiation coming can be approximated as a plane wave, basically. So the intensity we get from the red star at our telescope, so let's use IT, is just this 4 pi r s squared sigma t s squared divided times, no, divided by, yeah, divided by, sorry, I have to, for 4 pi uh, wait, what is the, how, yeah, 4 pi d squared, d4. Oh yeah, it is d4, not squared. Good that you said. This is a mistake I wouldn't have really noticed during the competition. So, so those 4 pi's cancel, and yeah, we have something like this. Okay, fine. And now this I'm thinking next. Then mm, the this has to basically be the same intensity with which the mirror reflects to the secondary mirror where the image is formed. So so the d we found, this is basically again the radius of the star, which was is linked to the diameter of the star. So we have the diameter um, uh, over the over the what is it called, over the diameter here. So we can actually say that these are related with like Ri over R naught is equal to F over D. So we have here R naught over D, so we have R naught over D is equal to F over Ri, which is things we can actually solve for. So I can uh, now reduce this to the information I actually know. No, the thing was that I was thinking, the thought process was here that I have things that I don't know, basically. Um, but then I remembered that I just had solved for the distance. Actually, I didn't solve for the distance. For some reason, I thought I was solving for the distance just then. Yeah, well, then I basically know those things. Doesn't really matter if I use them or not. Yeah, actually, I had a completely wrong thought. I don't need really this information. Um, Not really useful. Um, but now this will radiate with some power. Uh, A R S squared D squared sigma T S fourth to the fourth power. And then this image will concentrate with intensity, um, with an intensity, um, and then it will travel a distance of f, basically. No, no, wait. Just yeah, and then this is focused. Yeah, and because this light is focused, I can basically ignore. Yeah. So then this will get into a small area of pi Ri. Actually, I can just work directly with the diameters, I realized. So this would be 40, 4002. 4002, and this would be also 4002. And then the intensity with which with which no, actually, this is the power with which the thing, the image gets power, because this power is same through all of the image, not only the image of the star. And then the image of the star will radiate with blackbody radiation of um, sorry, this is not 4 DO squared, this is DO divided by 4. And then similarly it will radiate outwards with pi over 4 di squared, and this is the thing we solved for, and we can then input uh, our BDI squared is not exactly actually correct. That would assume that the image is sharp, but there's diffraction wasn't there. So pi over 4 uh, is the image Yeah, I'm not sure how that would work. Well, I can just approximate that it's approximately di, I guess. Doesn't really matter. Pi over the di squared. Uh, my brain doesn't work that well at this time anymore. Sigma t, which is the thing we want to find. I'll check the t image. So t image um, must be the same with the power above, written above. No, not 4D. No, if I take a break, I would go to sleep, and I want to finish this. Then the sigmas disappear, at least. And then the... Is there anything else? And the force disappear, at least. And then... we will have a P image, which I will still leave as 4, is equal to di over do squared a, and 1 over d squared a ts 4, and 1 over pi, and di over do we basically solved is f over d. Do di over do. Sorry, this should be exactly the opposite way. Di over do, and this we solved to be d over f basically previously from the image law. So then we have t image 4 is equal to, and the only thing that survives from that is f. So we have a over f squared pi over ts4. So we finally have the image I am very bad at writing image ts fourth power of a over pi over f4, and then we just substitute relative 3600 Kelvin times uh, 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 oh yeah, times A, which was 25, divided by pi uh, times, was it 150? 130. Well, 130 squared, and all of this 1 per 4. What did I write here? So about 530 Kelvin. It will, in reality, it will be a little bit smaller, or it can be even like much smaller if we take into account the diffraction, but I'm not really sure how to take into account the diffraction. Like, what factor would I get? The answer sheet. E0 a pass do I still have? Well, there's the D. Well, yeah, maybe. Well, probably. I'm still annoyed about the permanent magnet. This problem because I'm pretty sure I can solve that problem, but yeah, it's too late. I'll solve it later, probably tomorrow, for myself. But if you're interested, I can also post my solution to the Discord server as well. But yeah, let's continue. The absorption of a photon by the CCD camera leads to the emission of an electron within the apparatus. This occurs only if the photon has sufficient energy to excite an electron across an energy gap delta E. Assume that every photon with sufficient energy succeeds. Uh, yeah, okay. There is also leakage of electrons across the gap caused by the temperature of the CCD camera. This is the dark current ID and is measured in the number of electrons per second. It is a function of temperature according to that where I naught is a constant. The graph shows how dark current varies with temperature. The units are. Interesting that the graph should be like that. Well, temperature estimation can be pretty much gained directly from uh, this part. We just get rid of the 6, then we get an order of magnitude. Then the question is, how do we find that from this graph? I am pretty uh, I am I am relatively certain that this ID here. Actually, yeah, no, nothing. Well, it's pretty much a straight line, so I can probably do like again a Taylor polynomial approximation. Like let's do something like this: a Taylor polynomial approximation, because that would allow me to linearize in a way this graph, because normally how you would linearize this graph would be just to take a natural logarithm and graph that instead. But this is not what they have done, I believe. This is a no, this is a logarithmic scale, I just realized. So yeah. So then um, how does a logarithmic graph paper work again? I know how the scale works, but I'm just trying to think of the equation governing the transformation. It's like so this is pretty much like we have graphed ln of id, ln id, which is pretty much ln I naught plus or minus delta E over 6k bt, and because this is a logarithmic graph paper, this is like this is ln10 times 100 times no ln10, no 100s, no thousands, yeah, ln10 times the slope, and we see that the slope is like so if we go instead of this, we go like that every step here is like 1. Then when we change this into like like a proper logarithmic graph, then we have a change of basically well, like in, how can I say this? This is like 0.01 change over a change of 1, which is 100. So we get the slope to be k is equal to minus 100k. So then we get that delta E over kb is 6 times logarithm of 10 times that k, which is 100 Kelvin, and this gives us our approximation of the order of the magnitude. It's about 1400 Kelvin. Um, the electrons are collected in a capacitor, and at the exposure time the electrons are counted. There are three main sources of uncertainty in the process: a fixed uncertainty in the counting process called readout noise, a Poisson a distribution error associated with the dark current, and a Poisson distribution error associated with the detected incoming photons. Poisson distribution errors are equal to the square root of the number of counts associated with the process. The measured photon count is equal to the number of electrons in the capacitor minus the number of electrons associated with the dark current. Fixed counting process, readout noise. And the dark current, I'm just thinking about them, what the Poisson distribution. Number of counts associated with the process. Well, how many counts do we expect with the dark current? That is just like I dark current times some sort of characteristic time. Have we been given a characteristic time? Yeah, an exposure time, tau. and this is the plus. This is the error to do with. This is the error to do with the. I should probably copy this problem statement. This is the error to do with the counting of the dark current. B, because we will count ID times tau amount of dark current photon electrons, photons or electrons. I think it was electrons, basically, and we are given that the error is just the square root of that. And similarly, we expect the photon rate counting error to be exactly the same. And then errors are all, these are all independent errors, they don't really relate to each other, so we sum them in quadrature. So we will have the total error to be it was given sigma r plus plus id tau plus p tau, like that. That was a surprisingly easy problem, but that's for the remaining questions in this part, I assume the exposure time is 10 to the 4 and the readout noise is fixed at. Assume an operating temperature of 7.5 Kelvin, calculate the minimum photon rate P so that the photon count is 10 times the count uncertainty. I don't understand the question right now. Yeah, that photon rate. Yeah, now I understand. So 1 over 75 gives us 1.3. So we have about 10. So ID is about 10. ID is about 10. You know, by measuring. That ID is about 10. So now we will know that the photon rate is that the photon count is p tau, and we want that this is 10 times the uncertainty, which we just found out to be 1 plus id tau plus p tau. But this is not what we found out. We found out that this was the square root of that. And by raising everything to the second power, we will basically get squared 100 times this. So we will have So I'm just checking things. So yeah, then we will just have a quadratic equation. Actually, it will be much easier to solve for p to tau and then divide by tau. Well, okay, let's do that. Plus minus 100 sigma r plus id tau is 0. So tau p is equal to 100 plus or minus minus 4ac, so that will be 4 times 400 times sigma r plus id tau. So and this is all over 2. So now I can get that p is equal to p is equal to 100 plus square root of 100 squared minus 400. This is just like pretty basic stuff, so I'm not explaining much here. I hope you are able to follow it nevertheless, but don't really like this particular problem, and that's probably what you hear in me. How is this still undefined? I find that hard to believe. Yeah, that should be correct. Actually, I can see how, but that shouldn't be minus, that should be plus. Divided by tau, which was something like times 4. Well, that sounds a bit too high to my tastes. Because you did expect this to be quite small, so like I agree with the order of magnitude of this. This is fine-ish, but that is because I forgot to divide this by. So about 0.6. Zero 0.6. photons per second. Assuming all photons are just capable of exciting an electron across the band gap, what is the intensity of the source of photons in B3 on the primary? So I'm not sure what. Just checking stuff. Yeah, it seems I'm getting like really tired. I'm not really sure. Unless we are still assuming like an operating temperature, but that doesn't really matter. Um, all photons are, yeah, I forgot. But that would be just be capable of exciting an electron on the pixel. So if we use the same order of magnitude approach as before, then we have like the 1400K uh, so actually wasn't this pretty much I write it somewhere, yeah. So delta E uh, has to be like this type of stuff. Um, so yeah, I can solve delta E basically from wait a second. Yeah, I can solve a delta E from that. So it's the temperature times of the star, which we already solved, times KB, which is something like 380 Kelvin, and then I have to check the um, check the what is it called? The physical constant list is on my second screen. It's about times 1.38. 1.38 times 10 to the negative 23 joules per Kelvin, and this gives us an 300. Wait a second. Yeah, it was 138 something something. Yeah, I just forgot. My brain is like working on its own, and I'm not like functioning anymore at all. But I guess it's fine, because this gives us like, well, not that much if I look at that. And then I have to think about how many this is like the individual energy of that photon, so I can actually just put like E gamma here, and then were we given some other, assuming all photons, because then we would have to find out how many photons we receive per second, and I'm not sure if we should use the um, thing we calculated, or if we, yeah, we probably want to use the thing we calculated, which is like what did we calculate for it? 0.64. So that tells me that E per T, E per P is pretty much what I want. That is the amount of energy received per second, and then we just have to divide this by the area of the mirror, so we get the intensity from that. So we get something like this, and this was like 1.9 10 to the 20 joules per. No. I made it wrong. This should be EP over A, and the P goes here as well, times 0.64 divided by 25 meters per squared, and then we get the answer about 4.8. Finally. So this is just like a marathon to see how long I can solve. But I think that I don't know if I'll do specifically another live stream, but I may do a video about the rest of the problems, because I have to go to sleep. I think you can hear it from me that I do not function properly anymore. So I'll leave C and D and C2, so the theoretical 1 C2 and theoretical 2 parts C and D for tomorrow, and I'll do them then. So thank you if anyone who's still watching, and I'll just do the rest of the problems probably tomorrow, then make a video, or maybe I will live solve, I don't know. But right now it's like 11:30 p.m. right now, so I'll go to not sleep yet, but my brain isn't suited for for solving anything anymore. So